Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. We begin in darkness. Before any star set the heavens alight, before any galaxy took shape, there was a deep and endless night. We remember it, the universe in its infancy, all energy and matter spread thin, yet no light to break the blackness. In that primeval silence, there were no stars, no galaxies, only a cooling fog of hydrogen gas, invisible and waiting. The cosmos was dark, and it would remain so for ages, a vast ocean without islands, a night without memory. Yet even in that darkness, the seeds of light were present. Tiny ripples of gravity, left by the birth of the universe itself, were drawing matter together, slowly, silently. In the void, unseen clouds of gas and halos of mysterious dark matter gathered and grew denser. Time hardly had meaning in this eternal midnight. But at some point, perhaps a few 100 million years after the beginning, change arrived. In pockets of the darkness, the first fires kindled. Deep in those dense halos, gas clumped until pressure and heat ignited the first stars. One by one, brilliant newborn stars pierced the cosmic night like embers in a vast, dark sea. Their light was faint at first, much of it absorbed by surrounding clouds, but it grew. More stars burst into existence, and around them began to form the first primitive galaxies, a cosmic dawn after the long darkness. We remember the moment the lights came on. A firestorm of starbirth swept through the young universe, the first galaxies assembling as clusters of glittering light. What had been an endless silent dark became a realm of scattered gleams. Imagine it, the newborn cosmos, less than 1 billion years old, sprinkled with the glow of infant galaxies. Each was like an island universe adrift in a black sea, isolated and alone, yet bravely shining. These first galaxies were much smaller and simpler than the grand spirals and ellipticals that would follow. They flickered pale and red, their light stretched and dimmed by eons of travel. But however faint, they were beacons, the first organized realms of stars, announcing that the long cosmic night was ending. From where we stand now, nearly 14 billion years later, we can still catch glimpses of those early faint galaxies with our most powerful telescopes. They appear as tiny smudges of light in deep field images, ghostly and ancient. Many have long since grown or merged or dissipated, but their ancient glow still travels the universe, telling the story of when the cosmos first lit its candles. In that epoch, the universe was only a few % of its current age, a toddler cosmos taking its first steps into illumination. The darkness fought to hold on, absorbing and scattering the first starlight. But starlight is persistent. It ionized the fog around it, burning holes through the murk. Gradually, the black curtain lifted. What had been a cold, neutral haze became a transparent window. The era astronomers call the cosmic dark ages yielded to the cosmic dawn. We, the living cosmos, remember this transition. It was the first time light had structure and form. It was the moment the universe began to perceive itself in the mirror of starlight. The first galaxies were the universe awakening to its own possibilities, each a tiny island of something rather than nothing. In those islands, countless suns would soon forge heavier elements, explode, and seed space with the ingredients for planets and life. The story of everything we know, stars, planets, potential life, began with that emergence of galaxies from darkness. Out of utter night came the glimmer of countless distant candles. This was the threshold of galactic dawn. Out of the void came light and pattern, as if the cosmos had dreamed in darkness and now opened its eyes. Scattered across unfathomable distances, the infant galaxies shone alone, unaware of one another, like solitary lighthouse beams sweeping an empty sea. They were the first galaxies, precious, solitary sparks, in a silent abyss. The universe, once a slumbering expanse of night, was now awake with faint starlight. In that fragile glow, the cosmos beheld its reflection for the first time. A mysterious, reverent hush falls over us as we recall this dawn, the moment we first illuminated the darkness, the moment when galaxies, and with them the seeds of everything to come, emerged and took their place in the vastness. Now, in the wake of that first dawn, we turn our gaze to a single galaxy to understand the wonders it holds. Each galaxy is a vast cosmic island, and like any island, it has its own geography and inhabitants. Picture one such island universe, perhaps like our own Milky Way. It is a great swirling city of stars. Hundreds of billions of suns blaze within it, swarming in a rotating disk like a giant glowing whirlpool. Gravity is the architect that binds this galactic city. It gathers stars by the billions and holds them in its grasp, preventing them from drifting into the void. When we look at a galaxy through a telescope, we see the collective glow of all those stars merged together. A luminous disk or an ellipse, or an irregular scatter of light. But within that glow lies structure, bright knots and cloudy bands that reveal the galaxy's anatomy. At a galaxy's center resides a dense concentration of stars, a nucleus or bulge. In a spiral galaxy, surrounding this bulge is a flat disk spreading tens of thousands of light years, where stars, gas, and dust orbit in orderly rotation. The disk often bears spiral arms, winding structures that pinwheel out from the center. These arms are not solid arms of material, like spokes. They are regions of slightly higher density that move around the galaxy more slowly than the stars and gas. As stars and gas orbit, they bunch up in these density waves, rather like cars piling up in traffic on a highway. The compression of gas in spiral arms triggers the birth of new stars, which is why the arms are studded with bright blue stars and pink nebulae, the telltale signs of ongoing star formation. Between the arms, older stars orbit more quietly. The galaxy's outskirts are generally fainter, with fewer young stars and less gas. Above and below the disk lies the halo, a sparse, spherical realm of very old stars and globular star clusters, tight, ancient stellar congregations, orbiting the galaxy's center in all directions. And permeating all these components is a massive halo of invisible dark matter, of which more later, extending far beyond the visible edge, whose gravity holds the galaxy together. Let us tour these components in turn. First, the stars. They range from hot, young blue giants that burn briefly in the spiral arms, to cool, red, ancient stars that populate the bulge and halo. Each star is a sun, with its own potential family of planets. The number of stars is staggering, 100 billion or more in a large spiral. If we could fly through the galaxy, stars would surround us like a glittering snowstorm, especially near the core, where they crowd close. But even in the outskirts, you'd never be far from a sun. Despite that, the distances are so vast that to an individual star, like our sun, its nearest stellar neighbors are several light years away, tiny points separated by great voids. A galaxy is mostly space, but the sheer number of stars fills that space with collective light. Next, the gas and dust. Strewn through the disk are immense clouds of gas, mostly hydrogen, and interstellar dust grains. This material is the raw ingredient for new stars. In a galaxy's spiral arms, these clouds are numerous and concentrated. Between arms, they are sparser. Dust, though only a small fraction of the galaxy's mass, has an outsized effect on appearance. It absorbs and reddens light. Along the Milky Way's plane, we see dark rifts where dust in nebulae blocks the light of background stars. Gas, on the other hand, often reveals itself by the light of stars embedded within it. For example, glowing ionized hydrogen clouds, H2 regions, that appear as pinkish patches, marking sites of current star formation. Surrounding the bright disk of stars and the faint glow of gas is something more elusive. Every galaxy is embedded in an enormous halo of invisible matter, dark matter. We call it dark because it emits no light. We infer its presence by its gravitational pull. This unseen halo outweighs all the stars and gas by a factor of 5 or more. It extends well beyond where the visible galaxy fades out, like a transparent sphere engulfing the luminous parts. Were it not for the dark matter's gravity, galaxies as we know them could not hold together. The outer stars would fly off, and the galaxies we saw form in the early universe might never have coalesced so quickly. Finally, many galaxies harbor an immensely dense object at their core, a supermassive black hole. In a typical large galaxy, this central black hole might be millions or billions of times the mass of our Sun, confined to a region no bigger than our solar system. It's an almost inconceivable concentration of mass. Most of the time, this black hole is relatively quiet, seen only indirectly, for instance through stars orbiting it at high speeds. But if gas funnels into it, the black hole can become a quasar or active galactic nucleus, blazing with energy and even shooting out jets. We will revisit this phenomenon later. All these components, stars, gas, dust, dark matter, black hole, together make up a galaxy's anatomy. They are bound by the invisible glue of gravity, moving in a cosmic choreography. The stars orbit in the galaxy's gravitational field. In a spiral disk, they move in circular orbits around the center. In an elliptical, they swarm in random elliptical paths. In the halo, they soar in elongated trajectories far above or below the disk before falling back. The gas flows in the disk, sometimes shocked into new patterns by spiral density waves or supernova blasts. The dark matter halo itself likely just provides a steady gravitational background, as it does not clump into stars. From afar, a galaxy may look serene, like a single smear of light, or a softly glowing ellipse. Up close, it is bustling with activity, stars being born and dying, gas clouds drifting and colliding, clusters orbiting, perhaps a black hole gently accreting matter or flaring. It is a dynamic breathing system. The beauty we see, those graceful spiral arms or that smooth elliptical light, is the composite of billions of individual lives and events playing out on colossal scales. In many ways, a galaxy is a cosmic ecosystem, with stars as its organisms, gas as its sustenance, black holes as both regulators and recyclers. Gravity holds it all in a delicate balance. Consider again our hypothetical traveler flying through a galaxy's disk. In the densest regions near the core, the sky would be awash with starlight, thousands of brilliant suns glittering in a small patch of sky, far more spectacular than any night on Earth. In the outskirts, the stars thin out. The night would grow darker, though the majestic band of the galaxy's plane would still stretch across the sky, a reminder of the greater structure one inhabits. If our traveler ventures further, above the disk into the halo, the view would shift. Most of the galaxy's stars would lie below like a flat, glowing spiral, and around the traveler, there might only be the sparse halo stars, and perhaps a globular cluster or two in the distance, lonely outposts of the galaxy far from its busy heart. This is the anatomy of a galaxy, a vast ensemble of matter arranged by gravity into a structure that is at once orderly in its overall shape and orbit patterns, and chaotic in the micro-detail of individual star motions and gas turbulence. It is a self-contained cosmos, with internal processes of creation and destruction set against the backdrop of the expanding universe. Not all galaxies are alike, however. As galaxies grew and interacted, they assumed diverse shapes and characters. Some became elegant spirals, others grew into sprawling ellipticals, and many smaller ones took on irregular, whimsical forms. In the grand cosmic menagerie, galaxies are as varied as the creatures in a primeval sea, spiraling, stretching, colliding, and twisting into different configurations. Their shapes are visible signposts of their histories. Spiral galaxies are the archetype we've already been exploring. They have pinwheel shapes, a flattened rotating disk with spiral arms, a central bulge, and often a bar of stars slicing through the bulge. Our Milky Way is one such barred spiral. Spirals are galaxies in their star-forming prime. Their arms, shining with young blue stars and dotted with pink emission nebulae, show that these galaxies still have plenty of gas to make new stars. The presence of dust in the disk creates dark filamentary lanes that outline the spiral structure when viewed face-on, and that give edge-on spirals a shadowy mid-plane. 2/3 of spirals, including the Milky Way, have a bar structure, which is thought to redistribute material and perhaps trigger star formation by funneling gas inward. Spiral arms can be tightly wound or more open and irregular. Some spirals, called grand design, have well-defined arms that can be traced almost a full circle around, while others have fragmentary arm segments. Regardless of exact form, the hallmark of a spiral is a mix of star ages, hot young stars in arms, and older stars in the bulge and extended disk, and an ongoing cycle of star birth. Elliptical galaxies have a very different look. They range from nearly perfect spheres to elongated football shapes. Ellipticals typically show no spiral structure, no disk, and crucially, almost no cool gas or dust. Thus, they lack the neon signs of star formation, no blue young star clusters or glowing nebulae. Instead, their light is dominated by older reddish stars. An elliptical galaxy often appears as a smooth gradient of light, brightest at the center and dimming uniformly outward, with little texture. The stars in ellipticals orbit in random directions, like bees in a swarm, unlike the coherent rotation in a spiral's disk. This suggests ellipticals likely formed by mergers of smaller systems. Imagine two spirals merging. Their ordered disks could be scrambled into one big cloud of stars, orbiting every which way. The largest galaxies in the universe are giant ellipticals found in cluster centers, which probably grew by consuming many smaller galaxies. Conversely, there are also tiny ellipticals, dwarf ellipticals, and dwarf spheroidals, only a bit bigger than globular clusters, often companions to larger galaxies. Without much gas, ellipticals have long since ceased meaningful star formation. They are largely in a passive, quietly shining state. Lenticular galaxies, SRO type, are something of a bridge between spirals and ellipticals. They have a disk, like spirals, often with a central bulge, but no spiral arms and very little gas or dust. A lenticular galaxy looks like a smooth disk or a bulge with a faint pancake around it. One might think of them as armless spirals or disk ellipticals. They likely form when a spiral galaxy uses up or loses its gas. For example, gas stripped by falling into a cluster or exhausted by star formation and feedback. The result is a galaxy that still rotates and has a disk structure, but no spark left to form new stars. Lenticulars often show dust lanes or rings, but no active HII regions. They tend to have intermediate colors, not as blue as star-forming spirals, not as red as ellipticals, although more toward the yellow due to aging stellar populations. If spirals are galaxies in their adulthood and ellipticals in old age, lenticulars are perhaps late middle age. The shape remains, but the youthful glow is gone. Irregular galaxies are those that defy the standard categories. They have no regular shape, neither a disk with arms nor a smooth ellipsoid. Many are small, dwarf irregulars, essentially blobs of stars and gas. They often contain significant amounts of gas and ongoing star formation, but in a haphazard pattern. The large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere, are irregular dwarf galaxies orbiting the Milky Way. The Large Magellanic Cloud, LMC, actually has a bar and one spiral-like arm. It's a magpie of a galaxy, part bar, part irregular disk. The Small Magellanic Cloud is more chaotic, an amorphous sprinkle of stars with no obvious center. Such irregulars could be young galaxies that haven't settled into a definitive form, or were perhaps normal galaxies distorted by gravitational encounters. Some irregular shapes result from collisions. For instance, the aftermath of two galaxies grazing each other might be an irregular burst of stars. There are also ring galaxies and other peculiar forms, like the cartwheel galaxy's bullseye shape, usually arising from special interactions. Irregulars demonstrate that galaxy formation can be messy. They remind us that not every galaxy gets to be a neatly structured spiral or a smooth ellipse. Some are cosmic driftwood, fragments still finding their form, or scraps left over from bigger systems. In truth, many galaxies evolve from one type to another. A spiral can merge with another and become an elliptical. A tidal encounter can turn a spiral into a distorted irregular, perhaps temporarily, before it resettles. Two dwarfs colliding might spark a mini-spiral structure. The classification is a snapshot of a galaxy's visible state, but underlying that state is a story. Even so, Hubble's classic tuning fork diagram, spirals branching into barred and unbarred, lenticulars in the middle, ellipticals on the handle, remains a useful map of galaxy diversity. Each shape speaks to physical conditions. Spirals mean a spinning disk with ongoing star formation. Ellipticals mean a gravitationally relaxed system that likely experienced mergers and lacks fuel. Irregulars often mean either youth or disruption. Across the cosmos, we see that early on, many galaxies were irregular and clumpy. Over time, through mergers and accretion, some settled into spirals. Others, especially after big collisions, became ellipticals. Thus, the shapes we categorize are also stages in a galactic lifetime, or outcomes of galactic interactions. Different shapes also affect what life inside might be like. A planet in an elliptical galaxy's outskirts might have a night sky filled only with a gentle, diffuse glow. No grand Milky Way band, since the stars are more uniformly distributed. In a dwarf irregular, the sky might be relatively dark, except where a local pocket of star formation lights it up. In a spiral like ours, we enjoy the spectacular band of the Milky Way and rich constellations, a product of living in a structured, starry disk. Yet beneath these varied forms, galaxies share a fundamental role. They are star factories. No matter the shape, virtually every galaxy at some point converts gas into stars. This ongoing creation process is the heartbeat of a galaxy's life. Let us turn to that internal activity common to all but the most dormant galaxies, the birth of stars within these island universes. Galaxies are cosmic furnaces where new stars are forged from interstellar gas. Deep within vast, cold molecular clouds in a galaxy's disk, gravity gathers pockets of gas until they ignite into stars. This happens continually in galaxies with available fuel. Spirals are especially prolific. They're giant molecular clouds, often tens or hundreds of light years across, and containing thousands of solar masses of molecular hydrogen, serve as nurseries for star clusters. Within such a cloud, small density enhancements draw in gas around them. As the gas compresses, it heats up. When a pocket, perhaps a few tens of times the sun's mass, collapses enough, the temperature and pressure at its core soar to the point that hydrogen nuclei begin to fuse into helium. At that moment, a star is born, a tiny thermonuclear furnace balancing gravity's inward pull with energy's outward push. The newborn star often emerges in a cluster with dozens or hundreds of siblings, all formed from the same cloud. The remaining gas may be blown away by the collective radiation and winds of those newborn stars, clearing out a bubble and leaving behind a shining cluster. Throughout a galaxy's spiral arms, this drama plays out in countless locales. For example, in our Milky Way, the Orion Nebula is one such stellar nursery. To the unaided eye, Orion's sword shows a faint fuzzy patch. Through a telescope, it's a glowing cavern of gas with a handful of massive young stars illuminating it. Those stars are mere infants, less than 1 million years old. And where we see the nebula's bright veil, many more protostars are likely gestating. The Orion Nebula is just one of many star-forming regions in our galaxy's Orion Arm. Star formation rates vary. The Milky Way forms roughly 1 to 2 sun-mass stars per year. In fact, mostly lower-mass stars. The high-mass ones are rarer. Some galaxies, especially in earlier cosmic times or in violent starbursts, form stars much faster. There are galaxies observed, often due to collisions or mergers, forming perhaps 50 or 100 suns per year for short periods. We call these starburst galaxies. They blaze with the light of massive young stars and are often veiled in dust that those same stars later blow away. Conversely, small dwarf galaxies or massive gas-poor galaxies might only trickle out a star or two per year, or nearly none if they've lost their gas. Galaxies self-regulate this star formation to an extent. When many stars form at once, the first massive ones, O-type stars, emit intense ultraviolet radiation and charged particle winds. They heat and push on the surrounding gas. Shortly thereafter, within a few million years, some of those massive stars explode as supernovae, sending shockwaves through the molecular cloud. These effects can compress some parts of the cloud, triggering more stars in a chain reaction, but can also disperse other parts, shutting down further star formation in that region. In a spiral arm, one often sees this sequence like a ripple. Moving along the arm, there's a dust lane, where gas is gathering, then bright emission nebula, where stars have just formed, then star clusters with no nebulae, the gas blown away. It's a beautiful choreography. The galaxy's rotation and wave pattern orchestrate cloud collapse, and the newborn stars then orchestrate cloud destruction, limiting the yield. Over a galaxy's lifetime, this cycle steadily transforms gas into stars. In doing so, it also enriches the galaxy with heavy elements. The first generation of stars in a galaxy may have been born from nearly pristine hydrogen and helium left from the Big Bang. They lived and died, manufacturing heavier elements in their cores and in supernova explosions. Those metals, astronomers call all elements heavier than helium metals, mixed into the galaxy's gas. Later stars then formed from slightly enriched gas, and so on. Thus, as the galaxy ages, its gas and new stars contain higher fractions of elements like carbon, oxygen, silicon, iron, the very elements that make rocky planets and ultimately biology possible. Our Sun, born about 4.6 billion years ago, is metal-rich. About 2% of its mass is elements heavier than helium, evidence that it is a late-generation star. The earlier generations, now long gone, bequeathed the ingredients that went into the Sun and Earth. In this sense, galaxies are not just star factories, but also chemical factories, minting the periodic table as they go. The star formation process in galaxies will continue as long as there is cold gas to convert. But gas is a finite resource within a galaxy. It can be used up, or expelled, or locked in stars. Large galaxies can sustain moderate star formation for many billions of years, while small dwarfs may consume their gas quickly or have it stripped away by interactions. When we look at galaxies, their colors give away their star-forming status. Blue-tinted galaxies are actively forming stars. Short-lived blue stars tint the light, whereas yellow-red galaxies have little star formation, their light dominated by long-lived reddish stars. Many spirals have blue spiral arms but a yellowish bulge, indicating active star formation in the disk, but an older population in the core. Ellipticals are uniformly yellow-red, having long ago ceased making stars. Our Milky Way, with its mix of blue and white along the arms and a yellowish center, tells us it's still in business as a star factory, though not a starburst by any means. In its suburbs, like our Sun's vicinity, new stars form at a leisurely rate. In contrast, consider a galaxy like M82, the Cigar Galaxy. It's undergoing a ferocious starburst likely triggered by interaction with its neighbor M81. In M82's core, stars are forming so rapidly that their combined winds and supernovae are blowing gas out of the galaxy in colossal superwinds, visible as filamentous outflows. It's a galaxy essentially heaving with the effort of birthing stars, and in doing so, it may be burning through its available gas in a cosmic blink, tens of millions of years, after which it will calm down, having spent its fuel. Thus, star formation is the heartbeat of a galaxy, sometimes steady, sometimes rapid and irregular. With each beat, new stars light up, and with them new possibilities. Perhaps planetary systems, perhaps life. Every star we see in the night sky, aside from a few exceptions like supernovae, is evidence of this ongoing heartbeat. Our own existence is tied to it. The Sun is a product of the Milky Way's star-making abilities, and our planet's raw materials were forged in previous stars. One day, far in the future, the Milky Way and other galaxies will run low on gas. Star formation will slow to a trickle and eventually almost stop, as we'll discuss when we consider galaxies aging. But for now, in this epoch, the universe is still rich with galactic star factories. Each pinprick of light in a distant galaxy's photograph could be the home of millions of newly formed stars or stellar systems coming into being. In a very literal way, galaxies create the light that fills the universe. They are the engines turning dark, cold gas into brilliant starlight, generation after generation. They have been doing so since the cosmic dawn, and the cumulative light of all those newborn stars over the eons has gradually lifted the universe out of darkness. While stars are being born throughout a galaxy's disk, another drama is unfolding in the galaxy's core. At the center of most galaxies, as we noted, lies a supermassive black hole. In quiet times, this black hole is an invisible presence, detected only by its gravitational influence. But when it feeds, it can outshine the entire galaxy and radically affect its surroundings. The interplay between galaxies and their central black holes is a vital theme in cosmic evolution. We find that the mass of a central black hole is closely correlated with the mass of the galaxy's bulge in spirals, or overall stellar population in ellipticals. For instance, our Milky Way's black hole is about 0.01% of the galaxy's total stellar mass, and that fraction holds similarly for many others. This hints that the growth of black holes and the growth of galaxies went hand in hand. They know about each other. How could that be? The answer is feedback. When a galaxy's black hole accretes a lot of gas, it enters an active phase, becoming what we call an active galactic nucleus, AGN, which in extreme cases is a quasar. In this phase, the region around the black hole emits tremendous energy. Gas spiraling into the black hole forms a superheated accretion disk, shining across all wavelengths. Magnetic fields can tap into the rotational energy and funnel some plasma into enormous jets that shoot out of the galaxy's center at near light speed. Meanwhile, intense radiation pressure from the disk pushes outward on the surrounding gas. In effect, the feeding black hole blows a cosmic wind. This energy output can have profound effects on the galaxy. It can heat the interstellar gas or even expel significant portions of it from the galactic nucleus. If the black hole's output is powerful enough, it can sweep the galaxy's bulge nearly clean of the cold gas needed for star formation. This is one way star formation can be quenched in a massive galaxy. The quasar or AGN phase pumps energy into the galaxy and halts the supply of cool gas. The black hole's growth thus self-regulates. Once it becomes very luminous, it curtails further fuel from reaching it and also shuts down new star birth in the inner galaxy. This is why we don't see galaxies with ridiculously overmassive black holes compared to their size. The black hole will have effectively shut itself off by clearing out its vicinity. During the early active times, the galaxy black hole duo can be spectacular. Quasars, seen in the young universe, were galaxies with incredibly bright cores, often disturbed or merging in appearance, suggesting that interactions funneled large amounts of gas to their centers, igniting both starbursts and quasar activity. These quasars likely blew out so much gas that their host galaxies soon ran out of fuel for both star formation and further black hole feeding. The quasar then faded, and the galaxy was left as a more passive, elliptical, or lenticular, full of old stars and with little gas, a veteran of a violent youth. Even in less extreme cases, we see AGN feedback at work. In clusters of galaxies, the central galaxy often shows signs that its black hole periodically inflates huge bubbles in the surrounding hot gas, observed as cavities in X-ray images. These bubbles rise and send gentle shockwaves into the cluster, preventing the hot gas from cooling down to form new stars. The black hole is effectively heating the environment enough to forestall a cascade of star formation that would otherwise happen as the cluster gas cooled. This phenomenon is observed in the Perseus cluster, Virgo cluster, and others, where beautiful filamentary structures in the hot gas correspond to past outbursts from the central AGN. Our own Milky Way's black hole, Sagittarius A, is currently faint. Its accretion disk is trickling only a bit of material. But not so long ago, cosmically speaking, it likely had a blazar-like episode. The Fermi bubbles, giant lobes of high-energy emission extending 50,000 light-years above and below the galactic center, are thought to be remnants of an outflow from Sagar A, perhaps a few million years ago. They testify that even a relatively small supermassive black hole can drive galaxy-scale phenomena when active. Thus, a galaxy's central black hole can be seen as a sort of power regulator. During formative times, it lights up and, through its winds and radiation, keeps the galaxy from overdoing star formation. Eventually, the galaxy and black hole reach an equilibrium. The black hole no longer has a deep reservoir of gas to feast on. Star formation slows down, and they settle into a quieter phase. When we observe a massive galaxy today that isn't forming stars, often we find a quiet but hefty black hole at the center, exactly as this co-evolution scenario predicts. It's remarkable. Something as tiny in size as a black hole's accretion disk can influence a whole galaxy tens of thousands of light-years across. It's like a gear in a clock, small but key to the whole mechanism. Black hole feedback provides a link between the very small, sub-parsec scales and the very large, galactic scales. Through it, the cosmos achieved a balance. Without it, models suggest galaxies would be too large and too blue, forming stars far longer than observed. With it, galaxies mature and stop growing after a point, aligning with what we see. In cosmic terms, we can imagine a kind of dialogue. As a galaxy's gas collected and stars formed, the central black hole grew. When the black hole became powerful, it said, "Enough," and blew out the remaining gas, both halting further star formation and starving itself. The galaxy, having been energetic and blue, became a more quiescent reddish system. We see the aftermath of this in the present universe's many red ellipticals and lenticulars. Our own galaxy hasn't undergone a major quenching. It's moderate in mass, but in about 4 billion years, when the Milky Way merges with Andromeda, our central black hole will likely feast on a lot of inflowing gas and could briefly become a quasar, perhaps helping to shape the merged galaxy that will result. Thus, the presence of central black holes and their ability to transform energy make them crucial to the story of galaxies. In youth, galaxies shine by the grace of star formation. In their energetic adolescence, some shine by the grace of an AGN. By old age, both processes wane, leaving a quietly shining population of stars and a dormant heavy heart at the center. Galaxies and their black holes are partners in this cosmic evolution, each influencing the other. Galaxies are not static islands. They are dynamic entities that are born, grow, and change over the vast history of the universe. From the first proto-galactic fragments after the Big Bang, to the majestic spirals and ellipticals we see around us today, galaxies have undergone significant evolution. They have accreted matter, collided and merged with one another, and transformed from active star-forming systems to, in many cases, quiescent assemblies of old stars. The story of a galaxy's life is written in its shape, its star content, and its motion. It's a biography spanning billions of years. In the beginning, as we recalled, the earliest galaxies formed when the universe was very young. They likely started as small clumps, dwarf galaxy-sized pieces drawn together by dark matter gravitational wells. These clumps were full of gas, which began forming the first stars. Early star formation might have been frantic, massive stars, short-lived, quickly enriching the surroundings with heavier elements upon exploding. Small clumps merged into bigger clumps. Through both chaotic mergers and smoother accretion of gas along filaments of the cosmic web, galaxies began to build up. Simulations of cosmic structure show that little galaxies, with masses perhaps 1 million to 1 billion times that of the Sun, formed first and then congregated to form larger ones. This process is sometimes called hierarchical assembly, like small bricks assembling into bigger structures. Our Milky Way, for example, has cannibalized many smaller systems over time. It contains star streams and outer clusters that are the remnants of devoured dwarfs. Even now, it's shredding the Sagittarius dwarf spheroidal galaxy, adding those stars to its halo. In the past, it likely did this multiple times. This is how a large spiral can grow over billions of years. Galaxies also grew by accreting fresh gas from their surroundings. In the early universe, gas was more densely and readily available, and galaxies could draw in cold flows from intergalactic space, sustaining high star formation rates. Around 2 to 3 billion years after the Big Bang, roughly the peak of cosmic star formation, often called cosmic noon, many galaxies were in a veritable growth spurt, rapidly forming stars, growing their black holes, and often interacting with neighbors because the universe was smaller then. Everything was closer together. Collisions and mergers are a dramatic driver of galactic evolution. When two galaxies merge, their shapes are profoundly altered. If a small galaxy merges into a big one, a minor merger, the big one mostly keeps its identity. Perhaps the event thickens the big galaxy's disk, or flings some of the small galaxy's stars into the halo, or triggers some extra star formation. But when two comparably sized galaxies merge, a major merger, the result tends to be an elliptical galaxy. The violent relaxation of stars' orbits during the merger randomizes their motions, and any cold gas present can be either consumed in a burst of star formation or expelled by feedback. Thus, the end product is an elliptical with little gas. Major mergers also tend to grow the central black hole efficiently, since gas is funneled to the center, possibly igniting a quasar that then blows out the remaining gas. We believe many of today's giant ellipticals form from such major mergers billions of years ago. Not every galaxy undergoes a major merger, though. The most massive ellipticals likely did, some multiple times, but many spirals, including perhaps our Milky Way, have had a relatively gentle history with only minor mergers. Such galaxies can retain their disk structure and continue forming stars gradually. The Milky Way has a mix of populations that tell its history. A thin disk of younger stars, a thicker disk of older stars, perhaps heated by past interactions, a halo of very old, metal-poor stars, some possibly from small galaxies it absorbed early on, and a central bulge that could be the result of an ancient merger or internal evolution of the disk through bar formation. Galactic evolution is also about the decline of available gas. Initially, galaxies had lots of fuel. By now, many have used much of it up or locked it in stars. As a rough trend, the universe's star formation rate has declined over the last 10 billion years. Large surveys of galaxies find that those in the past were, on average, forming stars at a higher rate than comparable galaxies today. This aging of galaxies means that the cosmic color palette, has shifted. In the past, galaxies were bluer, more hot young stars, whereas today, a larger fraction of galaxies are red and dead. Environment plays a big role too. A galaxy in a rich cluster might have been quenched earlier. The cluster's hot gas can strip the galaxy's cold gas as it moves, a process called ram pressure stripping, and frequent encounters can stir up the galaxy and cause it to lose its orderly disk structure. Indeed, cluster galaxies are dominated by ellipticals and lenticulars, suggesting that many spirals that fell into clusters lost their gas and transformed. On the other hand, galaxies in lower density environments, small groups or voids, have fewer interactions and often retain their spiral structure and star-forming ability longer. Our local group, containing the Milky Way, Andromeda, Triangulum, and many dwarfs, is a fairly low-density environment. We have evidence that neither the Milky Way nor Andromeda has had a major merger in the last 99 to 10 billion years, allowing them to remain spiral galaxies. However, they are on course to merge with each other in about 4 to 5 billion years. When that happens, the result will likely be a more elliptical-like galaxy, sometimes nicknamed Milkomeda. Star formation may initially spike during the collision as gas clouds slam together, but eventually, much of the gas will either be used up or thrown out, and star formation will wind down. The merged galaxy will settle as a large, somewhat elliptical system with a very different night sky for any inhabitants. No clear disk band, perhaps just a diffuse glow of a central core, and an extended halo of stars. So the future of galaxies is, in a sense, written by their interactions. Over very long timescales, say 100 billion years or more, the continued merging of groups and clusters means many galaxies will coalesce into a few very large galaxies, especially as cosmic expansion drives distant ones out of reach. There's a concept that eventually gravitationally bound structures like our local group will merge into one giant galaxy, and beyond that, thanks to the accelerating expansion of the universe, that galaxy will be essentially alone, all other galaxies having receded beyond the observable horizon. But that far future scenario is speculative and far beyond any current age. In summary, the galaxy we see today is the product of billions of years of change. A spiral like the Milky Way was once smaller, likely a swarm of proto-galaxies coming together. It has grown by accretion and mergers, formed stars steadily, and will continue to change, especially with the impending Andromeda encounter. An elliptical in a cluster may have once been several disk galaxies that danced and combined. Even tiny dwarfs have stories. Some might be leftover building blocks that never made it into a larger structure, living fossils of the early cosmic times. Galaxies, therefore, have life cycles. They can be thought of in terms of birth, formation from primordial matter, growth, star formation and mergers, maturity, a steady state, often disk galaxies with ongoing star formation, and old age, exhaustion of gas, becoming passive. Not every galaxy neatly follows this, and some experience rebirth if new gas is acquired, but many do traverse from active to quiet. Our universe today contains galaxies in all these stages. When we look out in space, distance corresponds to looking back in time. Nearby, we see many ellipticals and gas-poor systems, galaxies that have largely completed their star-forming story. Far away, hence long ago, we see more irregular, clumpy galaxies furiously forming stars, the youth and adolescent stages. By combining those views, we piece together the saga of galactic evolution. Now imagine the large-scale arrangement of these galaxies. They are not scattered randomly like isolated birds. They congregate and form patterns on the grandest scales. Galaxies, along with galaxy clusters and superclusters, are woven into a cosmic web, a filamentary network that spans the observable universe. This is the imprint of the initial tiny density fluctuations from the Big Bang, amplified by gravity over billions of years. If we could zoom way out, far beyond our local group, beyond our local supercluster, we would see galaxies arranged in filaments and sheets, intersecting at dense nodes, clusters, with immense voids in between where few galaxies reside. This we call the cosmic web. It looks somewhat like a three-dimensional spiderweb or foam. Each filament might stretch hundreds of millions of light years and contain many groups and clusters of galaxies. At their intersections sit the richest clusters, like the Coma or Virgo clusters, teeming with thousands of galaxies. Between filaments are voids, huge cavities, 100 million light-years across or more, that have only a sprinkling of galaxies, truly cosmic emptiness. Our Milky Way inhabits a minor filament on the outskirts of the Virgo supercluster. Recently, astronomers gave our local supercluster the name Laniakea, meaning immense heaven in Hawaiian. We are pulled gently toward the dense center of Laniakea, the region of the Virgo cluster, but will likely never reach it due to the expansion of the universe acting on larger scales. The local group itself is a little cluster on a filament that extends out toward other nearby groups like the M81 group and the Centaurus group, all on the boundary of the Virgo supercluster complex. This cosmic web is mapped by surveying galaxies and noting their 3D positions. One famous survey, the Sloan Digital Sky Survey, created maps with over 1 million galaxies, revealing an astonishing foamy structure, long filaments and walls, like the Sloan Great Wall, a filament 1.4 billion light-years long, and huge voids such as the Bootes Void, where few galaxies dwell. It's fascinating to realize that on scales of billions of light-years, galaxies themselves are like atoms, gathering into these massive structures. Gravity is the sculptor of the cosmic web. Dark matter, which does not interact directly with light or normal matter except via gravity, began clumping first, forming a filamentary network under the influence of its own gravity. Normal matter, gas, fell into those dark matter structures. Wherever the dark matter density was highest at filament intersections, galaxies and clusters eventually formed from the cooling gas. Along the filaments, chains of galaxies emerged. In the voids, the paucity of matter left vast expanses nearly empty. One might imagine flying through the universe on these scales. For long stretches, you would traverse dark, relatively empty void, maybe passing an occasional lone galaxy or small group that inhabits a shallow density well. Then gradually, galaxies would appear more frequently, like approaching a metropolitan region. You might enter a filament. Around you, galaxies would pepper space in every direction, often clumped in groups. Further on, you could come upon a node, a cluster like Coma, where hundreds of galaxies swarm like bees in a hive, the ambient X-ray glow of hot gas suffusing the cluster. Exiting on another side, a filament might lead you onward to another cluster or spread out into a wall, a sheet-like arrangement dozens of megaparsecs wide, but relatively thin. To the human eye, of course, none of this structure is directly visible. We see it only by plotting galaxy positions, but an observer within a rich filament would see many galaxies in their night sky. Some might even be naked-eye bright if they're close enough, the way Andromeda is visible from Earth. In the heart of a cluster, the sky would be crowded with fuzzy glows of elliptical galaxies and maybe intense light from a central CD galaxy. In a void, the night sky might have far fewer galaxy smudges visible at all. An observer might not realize they're in a universe full of galaxies because most are so distant. This large-scale cosmic web continues to evolve. Over time, gravity will slowly pull filament galaxies toward the nodes, making clusters richer, while voids expand as matter drains out of them. However, the accelerating expansion of the universe, driven by dark energy, will counteract gravity on the largest scales, so the web might reach a sort of frozen configuration in the far future, where most structures don't grow much further because distant regions are receding too quickly to merge. Standing back, we can appreciate the cosmic web as the universe's grand design, the pattern underlying the distribution of galaxies. It's a bit poetic that galaxies, which themselves often look like webs of stars, spirals, are arranged in an actual web on a larger canvas. The phrase "connecting the dots" becomes literal. The galaxies outline the connections in this web. Now, an important component of that web and of galaxies' internal structure is something we mentioned earlier, but did not fully explore: dark matter. This is the unseen scaffolding that holds galaxies together and forms the framework of the cosmic web. It is the backbone of structure formation, yet it remains mysterious. We recall the evidence. Stars in the outer parts of spirals orbit unexpectedly fast. If visible matter were all there is, those outer stars should be moving slower, just as outer planets in the solar system orbit the sun more slowly, following Kepler's laws. Instead, galaxies' rotation curves flatten out. Stars far from the center orbit at roughly the same speed as those closer in. The logical conclusion is that there's much more mass spread out through the galaxy's halo than we can see, providing the extra gravity to keep those stars bound in fast orbits. Similarly, galaxies and clusters move as if there's far more mass in the cluster than the galaxies, and hot gas alone account for. Thus arose the concept of dark matter halos. Each galaxy is enveloped in a halo of dark matter, extending well beyond the visible starry disk or body. In the Milky Way, for example, our visible disk is 100,000 light-years across, but our dark matter halo may span 600,000 plus light-years. Most of the Milky Way's mass, 85%, is in this halo. We don't see it, we only feel it gravitationally. What is dark matter? We don't fully know. It could be a new type of particle, often theorized as WIMPs, weakly interacting massive particles, or something like axions. We have evidence it's not made of ordinary atoms. Observations of the primordial elemental abundances and the cosmic microwave background imply normal matter is only 5% of the cosmic energy budget, while dark matter is 27%. Dark matter doesn't clump into stars or planets. If it did, we'd see those objects gravitationally or via blocked starlight. Instead, it seems to form diffuse halos. One striking illustration of dark matter's reality is the Bullet cluster. Two galaxy clusters collided. The fiery crash of their normal matter, hot gas, can be seen in X-rays, slowed and squeezed at the center of the collision. But the galaxies themselves, mostly empty space, passed through and, here's the key, gravitational lensing maps show the main mass concentrations went through largely unimpeded, now ahead of the visible gas. The interpretation, the dark matter of each cluster, being collisionless, sailed through with the galaxies, whereas the gas, normal matter, interacted and was left behind. This separation of mass via lensing and normal matter via X-ray is a direct sign that the bulk of the mass is not in the gas or galaxies, but in dark halos. In galaxy formation, dark matter collapsed first into a web of filaments and halos. Without it, the gas alone, affected by pressure and radiation, would not have aggregated into structures as early as it did. Dark matter provided deep gravitational wells to collect gas and seed galaxy formation. Galaxies formed at the centers of these halos. Even now, galaxies live at the bottom of their dark matter halos, like luminous ships at anchor in an invisible harbor. As galaxies merge, their dark halos merge too, creating ever larger halos. In clusters, the dark matter halo of the cluster holds the member galaxies together. In our local group, the combined dark matter halo of the group might eventually encompass both the Milky Way and Andromeda and all satellites into one enveloping structure. Yet, despite making up most of the matter, dark matter is elusive. It doesn't emit light, so we cannot see galaxy halos directly. We detect them via rotation curves, via galaxy motions and clusters, via gravitational lensing, distant galaxy images distorted by foreground mass. We build detectors deep underground, hoping a stray dark matter particle might collide with an atomic nucleus and give a tiny signal. So far, no definitive detection, but the hunt continues. Living inside a galaxy's dark matter halo is imperceptible. It's like living at the bottom of a deep ocean of gravity, but one that is calm and transparent. We feel only the net effect. For example, our solar system's motion around the Milky Way is faster than it would be from visible matter alone, thanks to dark matter. Perhaps occasionally, a dark matter particle zips through us without a trace. They are thought to interact so weakly that trillions pass through your body each second with nary a hint. Dark matter doesn't collide with itself in the normal sense, so halos tend to be puffed out and roughly spherical. Non-collisional matter doesn't flatten into disks. This is why the luminous part of a spiral is flat, but the dark halo is spherical and much larger. In summary, dark matter is the silent, invisible partner in the cosmic dance. It forms the scaffold on which galaxies are built and the glue that holds them together. Without it, the elegant spirals might fly apart, and the cosmic web itself would be a flimsy network rather than the solid frame of the universe. Having this unseen mass everywhere gives the universe a hidden richness. When we gaze at a beautiful galaxy, we should remind ourselves that what is visible is only a small fraction, like the tip of an iceberg gleaming above water, with the bulk submerged. When we see galaxies cluster, we must imagine the great clouds of dark matter encompassing them, overlapping, merging, anchoring the cluster's gravity. We often call galaxies island universes, but even islands are connected beneath the ocean's surface by the shape of the ocean floor. And so galaxies are connected by the dark matter landscape. They ride the currents and settle into the valleys carved by this invisible mass. In the present day, dark matter continues to influence how galaxies move within groups and clusters, and how those structures evolve under cosmic expansion. So we have galaxies luminous and dark, the interplay of shining stars and unseen mass. This interplay is on display when galaxies collide. We move now from the serene picture of a single galaxy to the dramatic scene of galaxies interacting. Sometimes, galaxies do not remain isolated. Gravity draws them together, and they can collide and merge. When galaxies collide, it's a slow-motion dance lasting hundreds of millions of years. Their stars are so sparsely distributed that the chance of star-to-star collision is extremely low. Most stars just sail past each other. But the galaxy's structures, their disks, arms, and gaseous contents, distort and intermingle under gravity's pull. The result can be both destructive and creative. Destructive in that the original orderly forms, like spiral arms, can be stretched into tidal tails or completely scrambled. Creative in that the collision often compresses gas and sparks tremendous bursts of star formation, and eventually forms a new, often larger galaxy. Picture two spiral galaxies drawing near. As their halos begin to overlap, each feels the other's gravity. The nearer edges of their disks tug on each other. Tidal forces draw out long streams of stars and gas from each galaxy, throwing them into intergalactic space. These are tidal tails, graceful arcs that can extend tens of thousands of light years beyond the merging galaxies. One famous example, the antennae galaxies, NGC 4038-4039 in Corvus. They are two merging spirals that have flung out long tails resembling an insect's antennae. Within their overlapping region, a frenzy of star formation is occurring, gleaming blue and pink in Hubble images. Over the next few 100 million years, those two cores will likely coalesce into one remnant galaxy, perhaps an elliptical, and the tails may fall back or drift away. During a collision, the stars mostly act like collisionless particles. They change trajectories due to the altered gravitational field, but rarely hit each other. Gas, however, behaves differently. Gas clouds do collide, shock, and collapse. So galaxy collisions often trigger starbursts as gas is funneled and compressed. In the antennae, for instance, hundreds of young star clusters, some superstar clusters far more massive than any in the Milky Way, have formed due to the encounter. In another well-known pair, M81 and M82, the larger galaxy M81 pulled gas out of M82, inducing a massive starburst in M82, hence its bright red core and superwind. Collisions can also feed central black holes. Perhaps merging two disks drives gas to the center to light up a quasar, as likely happened in many quasars' histories. The shapes produced in collisions are diverse and often visually stunning. Aside from tidal tails, we see ring galaxies, like the Cartwheel Galaxy, where presumably a smaller galaxy punched through the center of a disk, sending outward a ripple of star formation that appears as a ring. Shell galaxies, ellipticals with faint concentric stellar shells, likely remnants of past mergers that settled in oscillating layers, and completely amorphous mergers where the entire system is a chaotic cloud of stars, eventually to relax into an elliptical. Galactic collisions also can fling stars entirely out of galaxies, creating intergalactic stars. In clusters, we find a diffuse light between galaxies, partly from stars stripped during close encounters or mergers. In our local group, our Milky Way's interactions with dwarfs have left streams of stars, such as the Sagittarius stream, orbiting independently. Each collision is a one-time, unrepeatable event, with unique outcomes depending on masses, speeds, angles, and gas content. But generally, two similar mass disk galaxies merging will produce a more spheroidal galaxy and cease most star formation, especially if the merger uses up or expels the gas. Many scientists think that's why giant ellipticals in clusters exist. They are essentially merger pileups of many former spirals and dwarfs. From the perspective of any beings within a galaxy during a merger, the night sky would change over millions of years. They might see a faint smudge of the approaching galaxy grow larger and more detailed. Perhaps new bright stars and nebulae would appear as star formation ignites. Over long times, the constellations would be disturbed as star positions shifted gravitationally. If they survived to the end of the merger, which any individual star likely would, since direct stellar collisions are rare, they might find themselves in a very different type of galaxy, perhaps lacking a clear disk or patterns, and their sky now filled with a diffuse glow rather than a crisp Milky Way band. Destruction breeds creation. The old forms of galaxies are destroyed, but new arrangements of stars and new stars themselves are born. Tidal tails created by one merger might later condense into dwarf galaxies, essentially giving birth to new smaller galaxies as byproducts of a big merger. In fact, some astronomers suspect that certain dwarf galaxies around giants could be tidal dwarf galaxies from past interactions rather than primordial objects. Over time, most galaxies will participate in at least minor mergers. Our Milky Way is currently cannibalizing some dwarfs as noted, and in the future will engage in a major merger with Andromeda. In about 4 billion years, Andromeda's disk will start to distort the Milky Ways, and by 5 to 7 billion years, they will likely coalesce into a single elliptical-like system, nicknamed Milkomeda. This merged galaxy may then eventually gather the other local group members. Farther down the line, billions of years later, it might even fall into the Virgo cluster, though cosmic expansion might prevent that. Nothing is truly static. Collisions highlight another feature. Galaxies contain a lot of empty space relative to their size. If two spirals were shrunk to the size of two frisbees and thrown at each other, one might expect a smash. But in space, even when their disks overlap, stars mostly miss each other because of scale. The frisbees in this analogy are loaded with grain of sand stars inches apart. Two thrown frisbees would result in many sand grains colliding. But in galaxies, stars are like grains, perhaps miles apart on those frisbees. Not a perfect analogy, but it gives a sense of the sparseness. Ultimately, colliding galaxies tend toward equilibrium. Eventually, the gravitational chaos settles into a new, stable shape, often an elliptical. The wild star formation consumes gas and then peters out. The stellar orbits randomize and the system becomes dynamically relaxed. What was two lively spirals becomes one big, perhaps complacent, elliptical. Destruction creates beauty. The antennae-like tails, the rings, the burst of nebulae, all transient loveliness in the cosmic theatre. Eventually that fades, and a more subdued form remains, carrying in its diffuse light the mixed heritage of its progenitors. We see many ellipticals with faint tidal features or multiple nuclei or other signs that they formed from mergers, ghosts of their past lives etched in starlight. Thus, galaxies not only live, they can also reproduce in a sense, two become one, spawning perhaps smaller offshoots in the process, like tidal dwarfs. The number of galaxies can change with time, in regions like clusters. Initially, many moderate galaxies merged into fewer large ones, galactic cannibalism. In our local group, the number of substantial galaxies will reduce from two major, Milky Way, Andromeda, to one. But the combined light and mass remain roughly the same, minus whatever is ejected into intergalactic space. Having considered this tumult of collisions and growth, let us return to a familiar vantage. Our own galaxy, the Milky Way, which has thus far led a somewhat quieter life, allowing life to arise here. We have seen how galaxies in general work. Now we focus on the specific characteristics of the one we call home. The Milky Way is a barred spiral galaxy with a disk over 100,000 light-years in diameter. It has a central bulge of stars, about 10,000 light-years thick, and a bar of stars about 25,000 light-years long crossing the bulge. From the ends of this bar emanate the spiral arms. At least two major arms, Scutum Centaurus and Perseus, and several smaller segments or spurs, like the Orion arm where our Sun resides. Our galaxy's total stellar mass is on the order of 100 billion suns. It's accompanied by a retinue of over 50 satellite galaxies, mostly dwarfs, and is itself part of the local group with Andromeda and others. We experience the Milky Way from within. On a clear night in a dark location, we see it as a milky band arching across the sky. That is our edge-on view of the dense galactic disk. Through telescopes, this band breaks into countless faint stars and dark dust lanes. Toward the constellation, Sagittarius lies the galactic center, about 27,000 light-years away, behind thick dust clouds that hide the nucleus in visible light. In that direction, the Milky Way band is widest and brightest because we are looking toward the packed central bulge and along several spiral arms overlapping. At the center, beyond visual reach, sits the Milky Way's supermassive black hole, Sagittarius A. We have mapped stars orbiting extremely fast there, up to a few thousand km, indicating a mass of 4 million suns in a volume no larger than our solar system, hence a black hole. Currently, SGR-A is quiet. It's not actively accreting much gas, so it's effectively dark. If it were feeding, we'd detect strong radiation from that region, X-rays, etc. As mentioned, evidence of past activity, the Fermi bubbles, suggests it's had active episodes. Surrounding the nucleus is the bulge, a roughly spheroidal swarm of older stars, many red giants among them. The bulge has a higher proportion of old metal-rich stars, and likely also contains the bar structure. The bar is basically a stretched bulge. Our vantage point, offset from the center, means we see the bulge as a widening of the Milky Way's central glow. The disk of the Milky Way is the dominant feature. It is fairly thin, about 1,000 light-years thick in the star-forming regions, thicker in older stars. It contains most of the gas, in forms ranging from hot ionized regions to cold molecular clouds and dust. Our Sun orbits within this disk, currently about 25 pc, 80 light-years, above the midplane. We bob up and down through the plane as we orbit. The solar system completes one orbit around the center every 240 million years, sometimes called a galactic year. We've likely done about 20 orbits since the Sun's formation, meaning the Sun has been in various parts of the Milky Way's arms and spaces between arms over time. Our galaxy's spiral structure has been discerned by carefully mapping concentrations of gas via radio observations of hydrogen and carbon monoxide and young star clusters. We know that it has a barred center from infrared surveys like COBE and Spitzer that penetrate dust. The major arms are the Perseus arm, outside our orbit, and the Scutum Centaurus arm, inside our orbit, wrapping around the galaxy. The Sun lies in a smaller spur called the Orion Cygnus arm, or local arm. This local spur connects the major arms and contains the Orion Nebula, the Carina Nebula, and other nearby star-forming regions. Our galaxy is currently forming stars at a moderate clip, a few M per year, mainly in the spiral arms. Notable star formation complexes include those in Carina, Scutum, Sagittarius, all toward the inner galaxy, and the Perseus arm, farther out. We also have ongoing star formation in the molecular ring about 4 kpc, 13,000 Li, from the center, which might be related to the bar's dynamics funneling gas there. The Milky Way's halo is a roughly spherical zone surrounding the disk and bulge. In this halo are the oldest known stars of our galaxy, some nearly as old as the universe, found in globular clusters and as solitary halo stars passing through. We have observed about 150–160 globular clusters orbiting the Milky Way. These clusters are dense, gravitationally bound spheres of ancient stars, typically 12 billion years old or more. They reside mostly in the halo, on random elliptical orbits, tilted at various angles to the disk. Harlow Shapley in the 1910s used the distribution of globular clusters. They form a roughly spherical cloud centered on the galactic center to infer the Sun's offset position and the size of the Milky Way, one of the first steps in understanding our galaxy's true scale. The halo also contains the dark matter halo mass. The stellar halo, visible stars, is tiny compared to the dark halo, but it's our tracer of the halo's extent. Many halo stars and globulars have very low metallicity, few heavy elements, indicating they formed when the galaxy, or its precursor fragments, was very young and mostly unpolluted by supernovae. Some might even predate the Milky Way, having formed in smaller progenitor galaxies that later merged into the Milky Way. The Milky Way sits in a neighborhood with dozens of other galaxies, the local group. Dominating our local group are the Milky Way and the Andromeda Galaxy, M31. Andromeda, slightly more massive and about 2.5 million light-years away, is a spiral galaxy quite similar in structure to our own, barred as well, with a vast swarm of satellites. The third largest member is the Triangulum Galaxy, M33, a smaller spiral, maybe 1/5 the mass of Andromeda, which might be a satellite of M31 or an independent member. Beyond these 3 spirals, the rest of the local group is composed of dwarf galaxies. Most of these are satellites of either the Milky Way or Andromeda, and a few lie in between. The Milky Way's notable satellites include the large and small Magellanic Clouds, 2 irregular dwarf galaxies visible prominently from the southern hemisphere. They contain active star-forming regions, like the Tarantula Nebula in the LMC, the most luminous star-forming region in the local group, and are interacting with our Milky Way. A stream of gas, the Magellanic Stream, stretches from them, drawn out by tidal forces. The LMC and SMC orbit the Milky Way at distances of 50 to 60 kpc, 160,000, 200,000 Li. Over the next few billion years, they may either merge with our galaxy or possibly be stripped apart. Other Milky Way satellites include dwarf spheroidal galaxies such as Sagittarius, Draco, Ursa Minor, Carina, Sextans, Sculptor, Fornax, and many discovered more recently, like Tucana 2, Reticulum 2, etc., found in data from surveys such as SDSS and DES. These are generally tiny, faint galaxies. Some have only a few million stars, and they often appear as barely detectable smudges of light in telescopes. They have little to no gas and are supported more by random motions of stars, not rotation, analogous to miniature ellipticals. They tend to reside within a few 100,000 light-years of the Milky Way, and some, like Sagittarius Dwarf, are actually in the process of being tidally disrupted by it. Indeed, the Sagittarius Dwarf, discovered in 1994, is wrapping around the Milky Way in a stream of stars, evidence caught in stellar surveys as an overdensity of certain tracer stars. Andromeda likewise has its cohort of dwarfs, like M32 and M110, two dwarf ellipticals right next to its disk, visible even in early photos by Messier, and many dwarfs discovered around it, such as Andromeda 1-2, etc., and the recent surprise of a thin plane of satellite galaxies seemingly aligned around M31. Triangulum, M33, is smaller and has only a couple of tiny companions known. The local group as a whole is about 3 million parsecs, 10 million light-years, across, and is gravitationally bound. The Milky Way and Andromeda are approaching each other. 110 kilolumsas inward motion on top of some transverse motion. The group itself is moving toward the Virgo cluster, but likely will not reach it due to cosmic expansion. The local group's center of mass lies somewhere between the Milky Way and Andromeda. These two giants orbit that center and each other slowly. This little family of galaxies drifts together in space. Inside it, galaxies can affect each other. Our Milky Way is clearly affecting and consuming some of its dwarfs. Andromeda has likely swallowed some of its own. Its halo contains many streams indicative of past mergers. Eventually, as noted, the two big ones will merge. Effectively, the local group will condense into one galaxy containing most of the stars of the current group. The local group sits at the edge of the Virgo supercluster. Just beyond our group, about 15 million light-years away, lie small groups like the M81 group, around the spiral M81 in Ursa Major, and the Centaurus A M83 group, around Centaurus A, a peculiar elliptical, and M83, a spiral. Further out, how 50 to 60 million Li, is the Virgo cluster itself, a massive cluster of 2,000 galaxies. Our local group is being gently tugged toward Virgo, the Great Attractor region, which also includes the Centaurus cluster, Norma cluster, etc. But we are not part of Virgo. Rather, the local group is like a little outlying suburb of that enormous cluster complex. The environment of the local group, relatively isolated in a cosmic filament, has allowed the Milky Way and Andromeda to retain their gas and spiral forms longer than they might have in a dense cluster environment. It's a quieter corner of the universe. Now, not all galaxies in the cosmos are large like the Milky Way or Andromeda. In fact, by number, dwarf galaxies dominate. These are galaxies with much smaller masses and luminosities, often just a few million to a few 100 million stars instead of billions. Some dwarfs are irregular, like the Magellanic Clouds. Others are spheroidal or elliptical. Dwarfs are the building blocks that, assembled together, formed bigger galaxies. Many dwarfs also persist as separate entities, especially around bigger galaxies as satellites, or in isolation in voids. Dwarf galaxies are intriguing. Because of their low gravity, they're susceptible to having gas stripped or blown out. Many dwarf spheroidals around the Milky Way have no gas at all. Likely, the Milky Way's tides or radiation long ago removed it, or internal supernovae winds expelled it. These dwarfs consist mostly of old stars and are very faint. They are also extremely dark matter dominated. For example, the Draco dwarf contains only a few million solar masses of stars, but perhaps tens of millions of solar masses of dark matter. Its stars move as if a lot of unseen mass is present. making it effectively a lump of dark matter with a frosting of stars. This makes dwarfs excellent test beds for dark matter theories on small scales. Some dwarfs are more like surviving siblings of big galaxies, having converted only a small portion of their gas into stars and hanging onto their gas reservoirs for a long time. The Magellanic Clouds, for instance, still have plenty of gas and active star formation. The LMC even has its own satellites, a mini-system. In the early universe, many dwarfs probably merged into larger systems, but those that didn't can be seen as fossils of that time. We might liken dwarfs to cosmic plankton, tiny, numerous, easily influenced by currents, tidal forces from larger galaxies, yet absolutely essential in the food chain of cosmic structure. Without dwarf mergers, many larger galaxies would not have grown so massive. Without dwarf galaxies as satellites, big galaxies wouldn't have some of their halo stars, captured from dwarfs, or their extended globular clusters. Some globulars could be the nuclei of dwarfs that were consumed. The space between galaxy clusters is filled with isolated dwarf galaxies too, some in the process of falling into groups clusters for the first time. These tend to be gas-rich because nothing removed their gas yet, and are forming stars slowly. Over time, they might either form a few more stars and remain small, or eventually fall into a cluster and get stripped to become an ultra-diffuse cluster member. One fascinating aspect: dwarfs can have difficulty hanging on to not just gas, but also metals. When a star in a tiny galaxy explodes as a supernova, the blast can accelerate gas past the dwarf's escape velocity, blowing heavy elements out into intergalactic space. So many dwarf galaxies have much lower metallicity than larger ones of similar age. They lost more of the metals their stars produced. In this way, dwarfs pollute the intergalactic medium, enriching the cosmic environment with elements that later might be incorporated into other galaxies or proto-galaxies. Thus, dwarfs, though small, play a role in cosmic chemical evolution disproportionate to their size. In our local group, the ongoing accretion of dwarfs by the Milky Way and Andromeda is an example of the galactic cannibalism that likely happened frequently in the past. The halos of large galaxies are essentially graveyards of smaller ones, strewn with their tidally torn debris. We see these as stellar streams in our halo, like the Sagittarius stream, GD1, PAL5 stream, etc. Andromeda too is laced with streams. Each is the remains of a dwarf galaxy or globular cluster consumed and assimilated. Over time, those streams will phase mix into the halo, becoming indistinguishable smears of stars, adding to the smooth halo light. While many dwarfs live as satellites, some are relatively isolated. For instance, the tiny galaxy Wolf-Lundmark-Melotte, WLM, on the outskirts of the local group a 3 million Li away, is a dwarf irregular that has led a solitary life, slowly forming stars, barely interacting with bigger neighbors. It gives us a glimpse of how a very small galaxy evolves on its own. In sum, dwarf galaxies are crucial pieces of the cosmic puzzle. They were the seeds of larger galaxies and remain the most common galaxy type by number. Often overlooked due to their faintness, they carry important clues about the early universe, the low mass end of galaxy formation, and the nature of dark matter through their extreme mass-to-light ratios. We, within the Milky Way, are currently treating our dwarf neighbors in a mixed way. Some we nurture. The Magellanic Clouds are being drawn in and likely eventually will mix with us. But for now, they're triggered to form stars maybe by our tidal influence. Some we have torn apart, Sagittarius, and others orbit peacefully for now, Fornax dwarf, etc., which still have some old stars and even globular clusters of their own. In a few billion years, if any distant future astronomers compile a census, they might find that what was once dozens of dwarfs became just stellar streams in an enlarged Milky Way halo. Now, galaxies not only consume matter and form stars, they also breathe, in a sense. Massive stars and active nuclei can drive galactic winds, outflows of gas that extend far beyond a galaxy's main body. Through these winds, galaxies can expel some of their content into intergalactic space, influencing their surroundings and regulating their own growth. In a star-forming galaxy, especially one experiencing a starburst, the combined effect of many supernovae and stellar winds can create a superwind. We see a dramatic example in the Cigar Galaxy, M82, which we encountered as a starburst triggered by interaction. M82 shows twin reddish plumes of gas billowing out perpendicular to its disk. This is a galactic wind. What's happening is that thousands of supernovae from the central starburst have heated and propelled gas outward. This gas, a mix of hot plasma and cooler entrained material, is leaving the galaxy's gravitational grasp. Some of it might fall back later, but much may escape into intergalactic space. Along with gas, metals, carbon, oxygen, etc., are carried out, meaning the galaxy enriches its environment. Galactic winds are crucial in galaxy evolution. They can remove gas that would otherwise form more stars, effectively putting the brakes on star formation, especially in smaller galaxies where the gravity is weaker. It's easier for a wind to evacuate a dwarf galaxy than a giant one. This is one reason dwarfs often have low star formation rates or shut off early. They lost their gas to winds. Even in large galaxies, winds, often aided by an active black hole's energy output, can clear out the central regions and halt star formation there, leading to the kind of gas-free bulges we observe. Winds also disperse the ashes of stellar furnaces, the heavy elements. The intergalactic medium in galaxy clusters is observed to be enriched with iron and other metals, likely supplied by winds from member galaxies' past starbursts and outflows from active nuclei. In the early universe, before clusters existed, proto-galaxies likely blew metals into intergalactic space, seeding the raw primordial gas with heavier elements. So galactic winds are like the breath of galaxies that pollinates the cosmos. Another aspect is that winds can interact with a galaxy's surroundings. In a cluster environment, one galaxy's wind might slam into the intracluster medium, producing shocks. We sometimes observe X-ray or radio features in clusters that correspond to past winds or jets. In the cosmic web filaments, winds from galaxies can spread metals along the filament, enriching gas that might later fall into other galaxies downstream. Our Milky Way has modest outflow activity now, but evidence suggests that it too has or had a galactic wind. Aside from the Fermi bubbles produced by past AGN activity, there's also a structure called the Galactic Chimney, or the Northern Chimney, a region above the disk where hot gas from widespread star formation in the past may have vented out of the disk. The halo of our galaxy contains traces of elements that likely came from past outflows. When enough gas is expelled, it can eventually cool and rain back down, a process called a galactic fountain. In some spirals, localized starbursts blow gas out, which later falls back in a gentle drizzle elsewhere, redistributing metals across the disk. The Milky Way's halo gas, detected in UV absorption lines, might partly be fuel that is slowly cooling and returning, or fresh infall from outside, probably a mix of both. All this breathing, outflow and inflow is part of the self-regulation of galaxies. Too much star formation? Winds blow out gas, slowing things. Later, if the galaxy is quiet, it might accrete more gas again from its surroundings, or the expelled gas might cool and fall back, allowing a new cycle of star formation. This feedback loop helps explain why galaxies don't use all their gas at once in a single burst, except perhaps extreme starbursts, which essentially do and then become dormant. In the big picture, galactic winds are one of the mechanisms linking the small scale of stars to the large scale of galaxy groups. They enable material and energy exchange between a galaxy and the intergalactic medium. Through winds, galaxies essentially communicate with the universe, sending out signals in the form of enriched gas and receiving, in turn, sometimes pristine gas later. So we have painted a portrait of a galaxy's internal life, stars forming and dying, black holes growing and regulating, gas being cycled and sometimes expelled. Galaxies are not closed ecosystems. They interact with their environment gravitationally and through these winds and outflows. Let us now step back to a more distant time, when galaxies and black holes were in their most exuberant phases. In the young universe, quasars and active galactic nuclei were far more common. A quasar, short for quasi-stellar object, is the extremely luminous core of an active galaxy, powered by rapid accretion onto a supermassive black hole. During the peak quasar epoch, roughly 10 to 12 billion years ago, many forming galaxies shone as intensely bright quasars, visible clear across the universe. Quasars are among the brightest objects in existence. Some radiate the power of trillions of suns from a region no larger than our solar system. The nearest quasar to us, for instance, is dozens of times farther than Andromeda, yet can be seen in modest telescopes as a faint star-like point. And more distant quasars, whose light began traveling to us when the universe was only a billion years old, are detectable because of that immense luminosity. These beacons signaled that massive black holes were rapidly devouring matter in early galaxies. Often, quasars are associated with disturbed, merging galaxies, hinting that a collision funneled gas into the nucleus. The incredible output of a quasar is multi-wavelength, visible light, ultraviolet, X-rays, infrared. The accretion disk emits a broad spectrum. Quasars also often produce jets that emit radio waves. Some of the first quasars were discovered via radio surveys. Observationally, a quasar appears star-like, hence quasi-stellar, because at tens of billions of light-years, the host galaxy's extended light is too faint to see. Only the brilliant core registers. It was through spectroscopy that astronomers in the 1960s realized these star-like objects had enormous redshifts, implying they were incredibly distant and thus incredibly luminous to be visible at all. That realization expanded our understanding of both galaxies and black holes, revealing that some galaxies in the distant past went through a quasar phase. As the universe aged, quasars became rarer. Why? Likely because the fuel supply at galactic centers became less abundant once major mergers became less frequent and most central black holes had reached a satiation point. The quasars we do see nearby are relatively less powerful AGN, or are cases of a late accretion event. For instance, a galaxy might reignite its nucleus by swallowing a gas-rich dwarf. Active galaxies come in various forms: quasars and Seyfert galaxies, active nuclei in spiral galaxies, radio galaxies, ellipticals with huge jets and lobes of radio emission, blazars, AGNs whose jets point directly at us, making them appear especially variable and bright in high-energy output. All are manifestations of the same engine, accretion onto a supermassive black hole. The differences are often in orientation and scale. A unified model suggests that a quasar and a radio galaxy could be the same type of object viewed from different angles, with or without seeing the jet, etc. These active phases likely have finite duration, maybe a few million to tens of millions of years for a quasar-level episode. Some galaxies may have undergone multiple episodes if conditions allowed, e.g. periodic infall of fresh gas. In fact, our Milky Way's center might have flickered as a weak quasar for short spurts when it had access to enough gas. The evidence of past activity hints at that. What do quasars mean for galaxy evolution? As discussed, they are an extreme form of AGN feedback. A powerful quasar can blow out the bulk of a galaxy's gas, effectively truncating star formation. So quasars likely mark the end of growth spurt for their host galaxies, a sign that the galaxy has accumulated a large black hole and is now clearing itself out. It's like a candle flaring brilliantly just before it exhausts its fuel. From a cosmological standpoint, quasars are useful beacons for studying the early universe. Their light, traveling billions of years, carries information about the intergalactic medium it passed through. We see absorption lines from intervening gas clouds in quasar spectra, which has told us about the distribution of matter in the young universe, the rise of cosmic metals, and the epoch of rionization, the tail end of the Dark Ages, when early light sources rionized hydrogen. The farthest known quasars, with redshifts around 7.5, universe age, 700 million years, challenge our understanding. They have black holes, 1 billion solar masses already, meaning black holes and galaxies can grow very quickly in the right circumstances, probably via rapid, direct collapse of gas and early mergers. As we contemplate other galaxies, especially those outside our immediate cosmic neighborhood, we might see many that no longer have quasars, but carry evidence that they once did. Perhaps an oddly low gas content, or an overmassive black hole relative to their current size. The imprint of that active past can linger. We, collectively as a cosmic memory, look back at the epoch of quasars as a time when the universe itself was in a tumultuous youth. Galaxies were colliding frequently, star formation rates were high, and central black holes were feasting. It was a mysterious, energetic, almost violent phase, yet also one that seeded the calmer cosmos we inhabit now. Quasars, in their brilliance, helped bring an end to the era of universal star frenzy and paved the way for the mature galaxies of today. Now we shift focus to how we know all this, how we observe galaxies across light and time. We humans, tiny creatures within one galaxy, have managed to build instruments that extend our senses to the edges of the cosmos. Through them, we piece together the life stories of galaxies. When we look at a galaxy, we are also looking into the past. Light takes time to travel. When you see Andromeda tonight, you view it as it was, 2.5 million years ago, when early hominins on Earth might have just begun using stone tools. The farthest galaxies we observe appear to us as they were mere hundreds of millions of years after the Big Bang. Thus, astronomy is like time travel by vision. By observing more and more distant galaxies, we essentially watch the cosmic movie in reverse. Nearby galaxies show the present frame, far galaxies show earlier frames. Our primary tools are telescopes that capture different wavelengths of light because galaxies emit or absorb across the spectrum. With optical telescopes like the Hubble Space Telescope or large ground-based observatories, we see the stars and star clusters, the shapes of galaxies, and sites of active star formation outlined in high emission. Infrared telescopes, like the Spitzer Space Telescope and now the James Webb Space Telescope, can see through dust to reveal stars and structures hidden in dusty regions, such as the Milky Way's center or star-forming molecular clouds. Infrared also picks up the glow of cooler, older stars that dominate galaxies like ellipticals, and it can detect redshifted light from very distant galaxies that has been stretched into infrared wavelengths by the expansion of the universe. Ultraviolet telescopes, like Galactic, highlight the most massive young stars and thus pinpoint where star formation is happening in a galaxy. X-ray observatories, Chandra, XMM Newton, see the high-energy processes, accreting black holes in AGN, shining in X-rays, and hot gas in clusters or galaxies. Radio telescopes map cold gas, notably the 21 cm line of neutral hydrogen, and also synchrotron emission from relativistic electrons in magnetic fields, tracing things like jets and supernova remnants. Each wavelength adds a layer to our understanding. For example, optical images of a spiral might show a pretty pattern of arms and some dark dust lanes, but a radio map of the same galaxy might reveal huge spiral extensions of hydrogen gas beyond the visible disk, perhaps warps or streams connecting to neighbors. Ultraviolet might show that the outer disk has clumps of young stars beyond where optical light seemingly ends. Infrared might unveil a barred structure in the core invisible in optical due to dust. It's like examining an organism under different types of light to see different components, bones with X-rays, heat with infrared, etc. One of the most powerful techniques in observing galaxies has been spectroscopy. By dispersing a galaxy's light through a prism or grating, we see spectral lines, signatures of elements in stars or gas. From these, we measure velocities via Doppler shifts. We can thus gauge how fast parts of a galaxy rotate, leading to those rotation curves for dark matter studies. We can measure how fast galaxies themselves move relative to us, the redshift, which in the context of universal expansion tells us their distance. Spectra also reveal chemical abundances, e.g., the strength of certain lines indicates how much heavy elements the gas has. Thus we know, for instance, that dwarf galaxies typically have low metallicities compared to large galaxies. Combining imaging and spectroscopy across wavelengths, we have developed a fairly complete medical chart for galaxies. Their masses, their compositions, their star formation rates, their temperatures, color indices or spectra, their environments, and so forth. With that, we infer their histories. We owe much to telescopes like Hubble for visualizing the distant universe. The Hubble Deep Field in 1995, for example, was a long exposure on a tiny patch of apparently empty sky. The resulting image revealed thousands of faraway galaxies of all shapes and colors, a cosmic scrapbook of galaxy evolution. We saw tiny blue galaxies, probably distant irregulars or spirals in their star-forming prime, larger reddish galaxies, perhaps already formed ellipticals in the background, odd interacting pairs, chain-like clumpy galaxies, etc. This one picture revolutionized our appreciation of how many galaxies are out there, an estimated hundreds of billions in the observable universe, and gave a snapshot of galaxies billions of years ago. Recently, the James Webb Space Telescope, with its infrared vision, has begun to see even further back, identifying candidate galaxies at redshifts above 10, within 500 million years of the Big Bang. These are extremely faint, and often just red smudges or dots even to Webb. But their existence is exciting. They might be among the first generations of larger structures. Some have unusually high brightness or masses, prompting astronomers to recheck how quickly galaxies could have grown. Webb's early data hints that some galaxies got big surprisingly fast, which could challenge or refine our models of early star formation and dark matter collapse. Gravitational lensing has been another boon. Massive clusters can magnify and stretch the images of background galaxies behind them. With lensing, we have observed galaxies that would normally be too faint or small. For example, the galaxy dubbed Eärendel, after a Tolkienian name meaning morning star, was detected by Webb. It's a highly magnified image of what might be a single star or star cluster in a galaxy 12.9 billion years in the past, magnified by a factor of thousands by a foreground cluster's lensing. Likewise, Hubble found the most distant galaxy known, GNZ 11 at redshift HUD 11, via deep field imaging and spectroscopic confirmation, capturing it thanks to its relative brightness, possibly enhanced by lensing or an inherent starburst. The observable universe is limited, but within that horizon, our instruments have reached remarkably far. The edge of what we can see is basically defined by the faint afterglow of the Big Bang, the cosmic microwave background, at redshift L1100. We cannot see galaxies past a certain redshift because there were none before a certain time, and because beyond a certain point, space expansion carries them away, such that their light hasn't reached us yet. What does the edge of visibility look like? As discussed, the farthest confirmed galaxies and quasars are around redshift 7 to 10, the universe 500 million to 700 million years old. Beyond that, we expect only proto-galactic fragments and the first light of stars reionizing the universe. There's a race on. Can JWST or future extremely large telescopes detect galaxies at redshift 15, 20? Possibly not bright galaxies, but maybe hints of star clusters or supernovae in that era via some serendipitous events. With each improvement in technology, larger telescopes, better detectors, new wavelength windows opened, we peel another layer of the universe's story. In the coming decades, New observatories like the Rubin Observatory for optical surveys, the Roman Space Telescope, infrared wide field, great for finding early galaxies via lensing surveys, ELTs, extremely large telescopes, 30-40 mils class on the ground, and maybe one day missions like LUVOIR or HABEX could allow us to map out even more of the universe's galaxies and even take spectra of extremely distant faint smudges to definitively gauge their ages and compositions. In doing this, we must preserve humility. We see snapshots, and from snapshots, we reconstruct narratives. Sometimes a galaxy can trick us. Two galaxies superposed can look like one odd one, or a transient event can make a galaxy seem more luminous. But overall, the consistency of evidence gives us confidence in the broad strokes of cosmic history we've outlined. Our viewpoint from inside the Milky Way is both a blessing and a curse. Curse in that dust and our position make mapping our own galaxy challenging. We did not even know the Milky Way's spiral structure well until the mid-20th century. But blessing in that, we have a ringside seat to a galaxy's internal details. We can study individual stars in galaxies, at least our own and near neighbors, which is impossible in far galaxies. Thus, we use the Milky Way as a template to understand certain fine-grained physics and external galaxies to place the Milky Way in context. We see that our galaxy is just one of a vast population, typical in some ways, perhaps a bit above average in mass, but certainly not unique except to us. Using light as our messenger and time machine, we have observed galaxies through 13+ billion years of cosmic evolution. We've catalogued their variety and, in doing so, discovered our own origins. Every image of a distant galaxy is also an image of what our own might have looked like long before the Earth existed. In that sense, observing galaxies is a form of introspection for the universe. It is the cosmos looking back at itself through us, examining different chapters of its autobiography. As we push the boundaries of observation, we approach the edge of the observable universe. This is the maximum distance from which light has had time to reach us since the Big Bang. It's about 46 billion light-years away, not 13.8 billion, because as light traveled, the universe expanded. At that horizon, galaxies, or proto-galaxies, are seen at the very dawn of cosmic time, if at all. Beyond it, light from any object is still en route and won't arrive until the future, or, if beyond the event horizon set by accelerated expansion, perhaps never. Already, at redshifts around 1011, we observe galaxies that are basically at the limit of current capabilities. They appear as tiny red dots. Their light has been traveling 13.3 billion years. Those galaxies likely are small and just forming their first batches of stars. They might eventually merge to become larger galaxies later. We are seeing them in embryonic form. At slightly higher redshifts, 15 or 20, any stars or clusters might be even younger. Possibly we're talking about the first sizable star clusters forming, each perhaps too faint individually for us to see without extreme lensing help. Eventually, as we near redshift 1000, we hit the surface of last scattering. Before that, the universe was opaque plasma, so no direct photons can come to us from earlier times. Except neutrinos or gravitational waves potentially, but that's another story. So we have a cosmic photo album that starts around the birth of visible galaxies and continues to the present. What lies beyond our observable universe? Likely more of the same cosmic web, galaxies and voids extending indefinitely, or at least to some huge extent. But that region is forever inaccessible to us due to the finite speed of light and cosmic expansion. In a sense, those unobservable galaxies are like ghosts, real, but we will never see their light. It's strange to think that the universe could be vastly larger than what we can observe, containing countless galaxies forever beyond our horizon. However, within our horizon, we have what appears to be a fair sample of the universe's contents. The distribution of galaxies and their properties seem uniform on large scales. The cosmological principle, no special spot. so likely the observable portion is representative of the whole. We can, with some confidence, generalize that galaxies exist everywhere in similar ways. As time marches on, the edge of our observable universe moves outward. We catch light from slightly more distant regions. But concurrently, due to accelerated expansion, distant galaxies are moving away faster and faster. Eventually, there's a limit. Distant galaxies' light gets redshifted into oblivion or never reaches us if space expands too swiftly. In fact, billions of years in the future, an observer in our Milky Way, or its merged descendant, will see fewer and fewer external galaxies. Far-off galaxies will slip beyond detectability. Closer ones will eventually follow. Trillions of years hence, perhaps only the local group's merged remnant will be visible to its inhabitants. All other galaxies' light will have stretched beyond recognition or dropped below detectable levels. The universe will seem to them an empty, dark void with one galaxy, a very different cosmic vista than the rich one we enjoy now. But that far destiny is far beyond our concern. At present, we stand at a time when the universe's story is richly accessible. We can look back almost to the beginning and see evidence of those earliest chapters. We see the whole sweep, from primordial galaxies just lighting up, through the turbulent adolescent universe of quasars and starbursts, to the settled modern universe of grand spirals and ellipticals, and even hints of the quiet senescence to come in some galaxies. Galaxies also change internally over time. They age. We have already touched on this. Star formation slows as gas runs out. Stellar populations shift toward older, redder stars. An active blue spiral can become a passive red lenticular or elliptical. The universe's population of galaxies is undergoing an overall aging. The cosmic star formation rate today is about an order of magnitude lower than it was 10 billion years ago. Many galaxies that once were lively are now quiescent. We observe this directly. In clusters at moderate distances, a few billion years ago, we see more spirals and irregulars than in nearby clusters, where most galaxies are ellipticals/lenticulars. In the field, we see that the fraction of star-forming galaxies was higher in the past. The transformation mechanisms, mergers, environment, internal exhaustion, have gradually quenched many galaxies. An aged galaxy, like a massive elliptical in Virgo, is essentially a memorial to its youthful past. Its light is now mostly from low-mass, long-lived stars, orange K-giants, red dwarfs, etc. The O and B stars that once made it blue are gone. They lived short lives long ago. Without new stars, the galaxy has slowly reddened. In a sense, galaxies have colors akin to leaves. A bright star-forming galaxy is like a green leaf full of chlorophyll, young, vigorous, while a quenched galaxy is like an autumn leaf that's turned red-brown. The green, blue light of young stars is gone, leaving the oranges and reds of the older population. Some galaxies can be rejuvenated if they get new gas. For instance, a previously quenched lenticular might accrete gas from a companion or the intergalactic medium and reignite some star formation. But generally, once a galaxy becomes a large elliptical, it doesn't return to a spiral. Too much structural change and gas loss has occurred. Rejuvenation usually happens in smaller doses, like a very low level of star formation on top of an old population, often seen in S0 galaxies that have a few patches of star formation from some residual or acquired gas. As eons pass, galaxies will continue to fade. One can extrapolate, in about 100 billion years, with no major external influences, the Milky Way, if it hadn't merged with Andromeda, hypothetically, would use up much of its gas and form mostly red dwarfs. The bright blue stars it has now will be long gone. Even the Sun will be a white dwarf by then. The galaxy's luminosity would decline. Low-mass stars can burn for extremely long times, trillions of years for the smallest red dwarfs, so the galaxy would never go completely dark in the foreseeable future. but it would become very faint and mainly infrared, since red dwarfs emit in red IR. Planets and remnants might still orbit quietly, but the grand star formation nebulae and massive clusters would be distant memories. A truly old galaxy would be a sparse collection of slow-burning embers. Imagine, trillions of years hence, a lone red dwarf civilization looking out at a night sky where maybe only red and orange stars speckle the heavens and no Milky Way band, because the bright contributors to it have died out. That's a far extrapolation, but it is where aging leads. However, interactions can reset the clock for some galaxies. The Milky Way, for example, will merge with Andromeda and likely spark a wave of new star formation as gas clouds slam together, thus temporarily making a new blue generation of stars before settling down to red retirement. So galaxies can have multiple epochs of youth in a way, e.g., after a quiet period, a merger can make them briefly young again in terms of star content. These cycles complicate a straightforward age narrative, but overall, as the universe's expansion dilutes fresh infall and as available unmerged galaxies dwindle, rejuvenations will become rarer. Eventually, most star formation will wind down everywhere. In the present, we still see a mixture. Some galaxies are in their vigorous star-forming phase, especially many smaller ones and some big ones like grand design spirals. Others have already quieted down. This mix is part of the so-called galaxy bimodality. The cosmic population tends to split into blue star-forming galaxies and red quiescent galaxies, with fewer in between. This tells us that the transition, blue to red, can be relatively rapid on cosmic timescales, a few 100 million years perhaps to quench a galaxy via a merger or other means. Thus, a galaxy might spend a few billion years actively forming stars, then, after a quenching event, fade to red and spend tens of billions of years in that state. While galaxies change, the universe around them changes too. Expansion continues, and the balance between gravity and expansion determines whether structures grow or not. Currently, we are in a phase where expansion wins on the largest scales, so the cosmic web is sort of frozen beyond supercluster scales, and within those scales, gravity still slowly merges galaxies within bound groups/clusters. In the far future, each bound group or cluster will merge into one huge galaxy. So ironically, while individual galaxies fade, the average galaxy's mass may actually increase due to mergers, but those will be the last major ones. Now, shifting from physical changes to a more speculative realm, consider the possibility of life in other galaxies. As we look at the myriad galaxies, we cannot help but wonder, is there life out there? And if so, how abundant is it? We know life arose in one galaxy, our own, at least on one planet. Given the vast number of galaxies and stars, it seems statistically inevitable that many galaxies harbor life-bearing worlds. Each galaxy contains billions of stars and likely billions of planets. Even if only a small fraction of stars have habitable zone planets, the sheer numbers mean potentially millions of such planets per galaxy. And with billions of galaxies, well, the number of possible abodes for life becomes astronomical indeed. We, beings made of heavy elements, are direct products of our Milky Way's star formation and chemical evolution. The same processes have occurred in every galaxy, so the ingredients for life, carbon, water, energy sources, should be widespread. Life might have arisen independently in countless locales. It could be microbial, or it could, on some worlds, evolve complexity and intelligence. When we gaze at Andromeda, that large spiral many like to photograph, we are looking at possibly 1 trillion stars and perhaps several trillion planets. It would be the height of arrogance to assume none of those trillion stars hosts a living world. Perhaps on a planet orbiting a sun-like star in Andromeda's disk, beings gaze back at the Milky Way as a faint blur and have similar wonder about us. Yet, the distances are so vast, 2.5 million light-years between us and Andromeda, that any exchange of information is exceedingly unlikely, barring some science fiction-level technology. For all practical purposes, any life in other galaxies is isolated from us by enormous gulfs of space and time. Still, the idea that the universe could be teeming with life, consciousness, and even civilizations scattered among the galaxies is awe-inspiring. It transforms those faint smudges of light into potential distant homes. We have essentially no way at present to detect life in other galaxies. We can't resolve individual planets or even individual stars in most galaxies beyond our local group, except via special cases like gravitational microlensing events. But we can reason. The physical laws are the same everywhere. Chemistry is universal. There's nothing special about the Milky Way that would make it uniquely favorable to life. In fact, some researchers consider that large, active star-forming galaxies might occasionally have more hazardous environments, more supernovae, etc., whereas a quieter galaxy might be more benign. But life on Earth has endured supernovae and cosmic rays, so perhaps these are not strict barriers. One interesting point: galaxies with different histories might have different proportions of heavy elements, which could affect planet formation. Very metal-poor galaxies, like some dwarfs, might have fewer solid planets because heavy elements form the cores of terrestrial planets. The early universe's galaxies likely had only gas giants, if any planets at all, until first generations of stars produced enough metals. Now, in the modern universe, most large galaxies have enough metals for abundant rocky planets. So life's probability might have increased over time as the universe became more enriched. That suggests the universe may be more life-friendly now, at age 13.8 billion years, than it was at, say, age 2 billion years, simply because more chemical raw materials for life, like phosphorus, which comes from stars, or oxygen for water, etc., are available and planets are more common. If life is widespread, what does it mean for the cosmos? It means the universe has, in a sense, a way to know itself in many places. We on Earth are one small voice, but imagine countless others in distant galaxies, each observing their sky, maybe developing science, maybe sending out signals that will never reach another galaxy because of distance, but still, they exist. The universe could be filled with such points of light, intellectual light, one might say, each unaware of the others because of the enormous separations. It's a bit poignant. The universe could be bursting with life and intelligence, yet each island galaxy is mostly isolated, separated by oceans of space that likely cannot be crossed with communication or travel given known physics. It's as if each galaxy is its own closed ecosystem of life. If that's the case, then our efforts to find extraterrestrial intelligence might only succeed within our own galaxy, listening for signals, or perhaps one day sending probes to nearby stars. Contact with any intelligence in another galaxy is far beyond any realistic scenario. Signals would take millions of years, even if they were intentionally directed, which they likely wouldn't be, as there's no way for them to know we're here. So in practice, each galaxy's life forms must live out their existence without knowing for sure if they are alone in their galaxy, and certainly without direct contact with other galaxies' life forms. Nonetheless, just knowing that life likely exists out there can change our perspective. We can look at a galaxy cluster and imagine it may host billions of biospheres. It adds emotional depth to those points of light. It also humbles us. We are one tiny form of life on one planet, around one star out of 100 billion in one galaxy among billions. It's the ultimate Copernican extension. Not only is Earth not the center of the universe, our galaxy isn't either, and life, if common, is not centered on us. And if, by some chance, life is extremely rare, if it turns out Earth is one of very few cradles of life, then the burden on us is immense. We carry the flame of consciousness for the cosmos, perhaps a flame that flickers only in a few places. That would make the universe a lonelier place, and our role all the more significant, to cherish and propagate life and consciousness. Either way, the mere possibility of life throughout the galaxies casts the cosmos in a new light, a possibly living cosmos, or at least a cosmos with many oases of life. After contemplating these sweeping themes, the birth and death of galaxies, the rise of stars and possible life, we return to the personal perspective. We live inside a galaxy. What does that mean? It means when we look up at the night sky, we are looking through the lens of our galaxy's stars. All the starry sky we see is part of the Milky Way, except a few smudges, like Andromeda. It means the story of the Milky Way is our story. For a long time, humanity didn't know that those spiral nebulae out there were other galaxies. Only in the 1920s did Edwin Hubble and others prove that the Andromeda Nebula was far outside the Milky Way, settling the great debate and expanding our known universe enormously. Since then, our perspective has changed from thinking the Milky Way was essentially the universe to realizing it's one of countless universes within the universe. This awareness that we inhabit a galaxy among many is one of the profound intellectual revolutions of the 20th century. So, to live inside a galaxy is to know that the universe is much larger than our home. The Milky Way is immense on a human scale. 100,000 light-years is far beyond direct comprehension. Yet we know now it's just one disk among billions strewn through space. That can make one feel small, but also connected to a grander existence. We know our galaxy's place in the cosmic web, on the outskirts of Laniakea supercluster. We know its future, merger with Andromeda, eventual fade-out. We've pieced together its past, formation from smaller pieces, multiple bursts of star formation, perhaps a barred spiral structure forming later on. Thus, we have context for our own existence. We're not adrift without a cosmic address. We can say we reside in the solar system, which orbits in the Orion arm of the Milky Way, which along with Andromeda and others forms the local group, on a filament at the edge of the Virgo supercluster. When the cosmos is remembering itself, part of that memory is our emergent understanding of our coordinates in space and time. We've learned that heavy elements in our bodies were forged in the Milky Way's previous generations of stars. Effectively, we are children of the Milky Way. In a poetic sense, the galaxy made us, and now through our eyes and minds, it has become aware of itself. We often speak of, we are the universe experiencing itself. At a more localized level, we are the Milky Way experiencing itself. Tiny, conscious bits of the galaxy that can contemplate the whole. This perspective can instill a sense of belonging and unity. All humans are literally of one dust, cosmic dust from our galaxy's past stars. The light of the sun that sustains us is a typical star's light in the Milky Way. The constellations that our ancestors named are patterns drawn on the backdrop of our galaxy's disk and halo. Our fate, as beings and as a planet, is tied to the galaxy's fate. If, say, a supernova goes off close by, or the galaxy's nucleus had a dangerous flare, it could affect Earth's biosphere. Conversely, what we do on Earth has negligible effect on the galaxy at large. We're too small. Except perhaps one day, life from Earth might spread to other star systems, and thus the galaxy would have a new phenomenon. Interstellar life, a kind of galactic ecosystem spanning multiple stars, originated by us. That remains science fiction for now, but in principle, a galaxy hosting a spacefaring civilization might see life expanding within it, in a way seeding parts of itself with purpose. To live inside a galaxy also encourages a cosmic perspective that can be spiritually significant to many. When we see pictures of billions of galaxies and realize each is full of wonders, it can make everyday problems feel smaller and inspire a sense of unity with the cosmos. Many astronauts report a profound shift in consciousness, the overview effect, when seeing Earth from space, a fragile ball in the vastness. Multiply that to seeing the Milky Way from an outside vantage, which we can only simulate in our minds. One would see our galaxy as a spiral among others, and Earth an invisible speck. This could foster a deep sense of the preciousness of our world and the absurdity of human divisions. We are all riding this great galactic spiral together. In a very literal sense, our lives are bounded by the galaxy. The night sky's beauty, that milky band, is a constant reminder of the greater structure we belong to. We can't easily travel outside the galaxy. It would take an unrealistically long time with current or foreseeable technology to reach intergalactic space, so we will likely remain an intragalactic species for eons, if not forever. Our voyages will be between stars, not between galaxies, unless some exotic breakthrough in physics occurs. But that's fine. The Milky Way has plenty to offer. Think of the diversity within one galaxy. We have regions densely packed with stars, like globular clusters where skies are awash with starlight. Regions almost empty, like the far outskirts where a star's nearest neighbor might be tens of light years away, a dark, lonely void. We have neutron stars, black holes, planets, comets, nebulae, bright blue giants, tiny red dwarfs, an entire zoo of cosmic objects, all bound by the common gravity of our galaxy. We have the relics of ancient history, old stars with virtually no metals, nearly as old as the universe, and the promise of the future, protostars in dusty cocoons that will light up soon. We have cataclysms, supernovae occasionally lighting up. The last seen in our galaxy was over 400 years ago, but surely more have occurred hidden by dust or on the far side. And we have gentle stability. Our sun has been shining steadily for billions of years in a fairly calm part of the galaxy. When we consider everything, to live inside a galaxy is perhaps the most profound scientific realization we have. It situates us in the vastness. It invites us to think on scales far beyond the human, and yet to marvel that our minds can do so. We have used mathematics and physics, products of human thought, to decipher the workings of the entire galaxy we live in and beyond. In doing so, we, who emerged from this galaxy's stardust, have closed a loop. The galaxy has given rise to beings who can, in a way, know the galaxy. Now our journey nears its end. We have traversed from the darkness before galaxies to the emergence of the first islands of light. We examined the anatomy of galaxies, their varieties and inner workings. We followed their life cycles and large-scale patterns. We pondered the interplay of stars and black holes, the webs that bind them, the winds that carry their essence outward. We imagined the presence of life within them and our own place on one tiny world, circling one average star in the Milky Way. It has been a vast journey, outward and inward at once. Let us end with a moment of cosmic contemplation. Envision our Milky Way as seen from a distance. Say, from a vantage point far above the galactic plane, a few 100,000 light years out. You see the great spiral suspended in blackness. Its disk is a gauzy whirl of blue and white, mottled with darker lanes. The central bulge is a warm golden glow. Encircling it all is a dim halo studded with globular cluster sparkles. Perhaps you see the Magellanic Clouds nearby, small smudges orbiting their parent galaxy. Beyond, a spray of other galaxies, the members of the local group, dot the void. Now imagine you are the galaxy, not seen from outside, but feeling from within. The combined gravity of billions of stars, gas clouds, and dark matter holds you together. You feel the slow rotation, 100 million years per turn, like the heartbeat of a cosmic being. You remember when you were younger and gas-richer, and bursts of stars lit up your arms. You foresee a time when you'll be blended with Andromeda into a new form. But right now, you simply exist in a steady state, stars forming at a modest rate, stars dying occasionally in gentle or dramatic ways, a vast collection of worlds and wonders within. Around you, the universe expands, but you and your local neighbors are bound in your dance. Time flows. Eons pass, though you measure time in rotations and orbits, not in human years. You have no mind of your own to comprehend all this, but a part of you, on a certain small rocky planet, has developed curious, self-aware creatures who are collectively reaching out with their intellect to understand the totality of what you are. Through them, through us, you, the galaxy, have attained a voice and a consciousness that can describe you. In a poetic sense, we are the Milky Way gazing upon itself with wonder. One galaxy, still turning in the void, carrying at least one species that can reflect on what it means. Multiply that by billions for all the other galaxies, and we sense a cosmos, perhaps filled with meaning, or at least ripe for it. The void is not empty. It is the stage on which galaxies spin and shine, each a cosmos unto itself. And so we leave our narrative with an image, a lone spiral galaxy drifting in silent darkness. It doesn't know we're here, but we know it is here. We, the cosmos contemplating itself, feel a sense of reverence. The galaxy's stars continue to orbit lazily. A cloud of gas collapses somewhere into new suns. A distant cluster in the halo slowly moves along its path. The central black hole waits quietly for its next meal. The galaxy in that image is our own, the Milky Way, viewed from an impossible perspective, a grand pinwheel of starlight and mystery. Everything we have ever known, every person, every tree, every ocean, every mountain, is part of that faint glow. That galaxy is our home, and one day, far in the future, all that will remain of us is maybe a slight alteration in one of its stars, or the whisper of a radio wave traveling outwards. But the galaxy will continue turning long after we're gone, carrying the legacy of all who lived within it, in the changed chemical makeup of its gas, in the artifacts left on some planets, or simply in the fact that for a brief moment, one of its countless stars harbored thinking beings who marveled at the sky. The camera of our mind's eye pulls back further, and now the Milky Way is just one of many fuzzy spirals in a cluster. Further back, the cluster is just one cluster among many against the cosmic web lattice. But let's stop there. Let's focus again on our galaxy, one galaxy, still turning in the void, serene and majestic. The light from its stars takes tens of thousands of years to cross from one end to the other. The faint glow extends outward, fading into the black of intergalactic space. It rotates imperceptibly slowly. To our brief lives, it appears almost eternal and unchanging. Yet we know it is dynamic and alive with cosmic processes. In the quiet of the cosmic night, our Milky Way continues its stately rotation. We, tiny sentient flecks on a minor world inside it, can close our eyes and feel at one with this great wheel of stars. In our hearts, we carry its story, from darkness to light, from simplicity to complexity. A story written in the language of starlight across the vault of heaven. As the galaxy turns, we find meaning not in being central or significant in size, for we are neither, but in understanding and appreciating the beauty and grandeur that surrounds us. This is our galaxy, our home, one of billions, yes, but uniquely ours at this place and time. It drifts through the cosmic night, still illuminated by the myriad fires within, still creating new light. A part of the cosmos that once was dark has become light and aware. And as we conclude our long journey, we can step outside under the real night sky. The Milky Way arcs above, for those fortunate to have dark skies, a spectral veil of our galaxy seen from within. Every point of that veil is a star, many perhaps with planets, some maybe with life. We stand here, consciousness emerged from a collection of cosmic particles, looking up and out. We feel the whisper of the galaxy's ancient memory in that band of light. and we whisper back our understanding into the silence. In that exchange, the galaxy's light entering our eyes and our minds decoding its story, the cosmos remembers itself. We close with that image of the great spiral, turning silently, carrying the echoes of its formation and the faint songs of whatever lives it has fostered. One galaxy, among countless others, continuing its journey through the dark. A wheel of fortune, a wheel of stars, forever spinning, forever moving, and in its own way, perhaps, forever knowing, through the living beings that arise and gaze out from within. The lights dim on our narrative, but overhead the stars of the Milky Way still shine. The story of the galaxies goes on, and we have been part of it. We are part of it, forever connected to the universe that made us. The spiral turns in the cosmic night, and we turn with it, children of the galaxies, awake and full of wonder. In the silent depths of space, there are wanderers. From the faintest dawn of history, human eyes gazed upward at bright points of light that moved against the fixed stars. The ancients called them planets, meaning wanderers, imagining gods and myths trailing across the night sky. But beyond the poetry of ancient minds, what truly is a planet? It is more than a mere light in the sky. It is a world unto itself. Planets are the great wanderers of the cosmos, worlds shaped by fire, gravity, and ice, each with its own story, written in molten rock and swirling cloud, in howling wind and drifting snow. They are the children of stars, born from cosmic dust and pulled into spheres by the inexorable embrace of gravity. They orbit in darkness, illuminated only by the suns they circle, and yet each holds its own internal light. The warmth of formation or radioactive decay, the glow of volcanoes, the electric crackle of storms. They range from scorching spheres of rock to bloated giants of gas, from oceanic blue orbs to frozen balls of ice and stone. Some are ensconced in thick blankets of cloud, others naked under the cosmic night. Some, incredibly, are lonely nomads, drifting between stars with no sun to call home, true wanderers in eternal night. To be a planet is to dance in a delicate balance. It means to circle a star in a cosmic rhythm, held by gravity's tether yet ever, falling around the light. It means to be round, sculpted into a globe by one's own gravity, mostly smooth, yet often scarred by the battering of eons. It means to dominate a little corner of space, clearing a path through smaller debris. Planets come in families, solar systems, where each member plays its part in the celestial choreography. Our own family is the solar system, with the sun as the patriarch and planets as its heirs, moving in regal procession. Imagine drifting high above the plane of our solar system. Below, the sun burns as a golden beacon, and around it, like marbles on invisible tracks, the planets sweep through space. Mercury, closest to the sun, is a little burnt cinder racing along its tight orbit. Venus follows, wreathed in thick, toxic clouds reflecting sunlight like a jewel, hiding hellish heat beneath. Earth, our home, blue with oceans and white with clouds, teems with life, our oasis in the dark. Mars comes next, a ruddy desert with ghostly dust storms and polar caps of frost, whispering of a wetter past. Far beyond, a belt of asteroids forms a rough boundary, and then the giants take the stage. Jupiter, king of planets, streaked in bands of stormy color, guards a menagerie of moons. Saturn, with its shimmering rings of ice, elegant and enigmatic. Uranus, tipped on its side, rolling around the sun with a pale cyan hue. Neptune, deep blue and distant, where supersonic winds drive dark storms. And at the edge, small icy worlds like Pluto circle in shadow, blurring the line between planet and comet in the distant Kuiper belt. These are the known members of our Sun's family, 8 major planets by the modern definition. and a host of dwarf planets, and countless smaller bodies. Yet planets are not unique to our Sun. As our knowledge grew, we discovered planets orbiting other stars by the thousands. We realized our night sky is filled with other suns, each with their own retinue of worlds. Planets, it turns out, are abundant in the galaxy. Perhaps every star has at least one, and in total, they likely number in the trillions. Some of these exoplanets are familiar in outline, rocky Earth-like bodies or gas giants like Jupiter, but others are stranger than we ever imagined. Giants so close to their stars that their skies rain molten iron, or worlds locked in eternal ice, far from any warmth. There are even worlds that wander alone, rogue planets drifting in perpetual darkness, having been thrown free from their stellar birthplace. The cosmos is literally overflowing with planets of every kind, each a chapter of the grand story of creation. This journey will explore what it means to be a planet from multiple angles. We will trace the historical path, from ancient stargazers to the scientific revolution that revealed Earth as a planet, and the later discoveries of Uranus, Neptune, and Pluto's reclassification, a saga that redefined our cosmic perspective. We will visit the inner solar system, the terrestrial planets, small spheres of rock scorched or nurtured by the sun, each with a unique personality. Mercury's extreme heat and cold, Venus's runaway greenhouse inferno, Earth's living biosphere, and Mars's lost rivers and thin air. Then we venture to the outer solar system, colossal gas and ice giants with raging storms and delicate rings, and moons that might hide life beneath their icy crusts. We will meet the dwarf. Planets like Pluto, Eris, and Ceres, diminutive worlds that challenge our definitions and remind us how diverse planets can be. Beyond visiting each member of our solar family, we will delve into the processes that shape all planets. We'll witness towering volcanoes that spew fire and shifting tectonic plates that mold the lands. We'll examine impact craters, the scars of cosmic bombardment, and winds and water that erode and change landscapes over eons. We'll peer into atmospheres thick and thin, the crushing yellow haze of Venus, the thin, cold sky of Mars, Jupiter's banded clouds, and Titan's orange smog. We'll experience weather and climate extremes beyond any earthly storm, from Jupiter's great red spot that has raged for centuries to the 1,200 mile-per-hour winds of Neptune that whip methane clouds into streaks. We will also uncover the hidden magnetic fields and internal structures that many planets possess. Those invisible shields born from molten cores or metallic hydrogen that can deflect deadly solar winds, and the strange interiors where pressures soar and matter behaves in exotic ways. And as our voyage extends outward, we will leave the comfort of our solar system entirely to discover exoplanets in their astonishing variety. We'll classify these alien worlds, super-Earths, hot Jupiters, mini Neptunes, rogue planets, and more, and see how they broaden our understanding of what a planet can be. We'll ponder the conditions that might make a planet habitable, able to support life, and how scientists seek the faint fingerprints of biology on worlds light years away. Finally, we'll look ahead to future exploration, the upcoming missions and bold ideas to visit new worlds, to send robot emissaries or even humans to planets and moons, and to build telescopes capable of reading the atmospheres of Earth like planets around distant suns. And throughout this odyssey, we will reflect on philosophical questions. What do these diverse worlds teach us about our own existence? How has the study of planets changed the way we see ourselves and our place in the universe? In exploring alien worlds, we inevitably hold up a mirror to Earth and to humanity. So, let us begin where our ancestors once did, by seeking to understand the wandering lights in the sky, and in doing so, embark on a journey across the solar system and beyond. Our first stop is the story of how we came to know these planets at all, a tale of curiosity, observation, and the courage to question our place among the stars. From myth to discovery, a history of our understanding. For most of human history, planets were points of light, their true nature unknown. In antiquity, 5 wanderers were known: Mercury, Venus, Mars, Jupiter, and Saturn. These wandering stars were held as gods. Mercury was the quick-footed messenger, Venus the goddess of love, shining as morning and evening star, Mars the blood, red warrior, Jupiter the king of heaven, and Saturn the god of time. The sun and moon were counted among the planets in the old world view, and Earth was not a planet at all, but the fixed center of creation. In ancient Greece and Rome, and in civilizations as far-flung as Babylon, India, and China, elaborate cosmologies placed these 7 wanderers on crystal spheres or chariots circling the Earth. Their motions were mysterious but meticulously observed. Occasionally, Mars would retrograde, moving backward against the stars, confounding expectations. To ancient astronomers, the planets were divine oracles whose motions foretold omens and seasons, yet their physical nature remained a subject of philosophical speculation. Aristotle and Ptolemy believed in a geocentric cosmos, the planets, sun and moon revolving in perfect circles around an unmoving Earth. It took bold imagination and careful observation to break this geocentric spell. In the 16th century, Nicholas Copernicus proposed a revolutionary idea. The sun, not Earth, was the center, and Earth itself was just another planet circling the sun. This heliocentric model demoted Earth from its special pedestal and made it one of the wanderers. It was a radical, even heretical thought at the time, challenging both scientific and religious dogma. But evidence soon began to accumulate. In 1609, Galileo Galilei turned the newly invented telescope to the heavens and witnessed wonders that forever changed our understanding of planets. He saw that Venus goes through phases like the moon, waxing and waning in shape, which only made sense if Venus orbits the sun, not Earth. He discovered 4 moons circling Jupiter like a miniature planetary system, a clear sign that not everything revolved around Earth. And he observed the rugged mountains and craters on our moon, showing celestial bodies were not perfect ethereal orbs, but had landscapes and geology. Galileo's telescopic revelations gave tangible reality to planets as worlds, places that could be seen and studied, not just lights. With the Copernican paradigm taking hold, astronomers realized that Earth was a planet too, moving through space with the rest. This was a profound philosophical shift. Humanity had to accept that our world was one among many. Over the next centuries, the solar system's known architecture expanded. In 1781, William Herschel, scanning the sky with a powerful telescope, noticed a tiny disk rather than a point. He had accidentally discovered Uranus, the first new planet found in recorded history. At first, Herschel thought it might be a comet, but its slow, steady orbit revealed it as a planet beyond Saturn. The solar system now had 7 planets. The discovery of Uranus doubled the size of the known solar system and suggested there could be more unseen worlds farther out. Uranus's orbit itself held clues of something more. By the early 19th century, astronomers noticed Uranus did not move exactly as predicted. It was being subtly tugged by an unknown force. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that an 8th planet must be lurking farther out, its gravity perturbing Uranus's path. In a triumph of physics and astronomy, Neptune was discovered in 1846, almost exactly where the calculations predicted, by Johann Galle and Heinrich d'Arrest at the Berlin Observatory. Neptune was dim and distant, invisible to the naked eye, yet the power of human reasoning had brought it to light. Now the known planetary count was 8. Around the same period, another kind of planet was found in the gap between Mars and Jupiter. In 1801, Giuseppe Piazzi discovered Ceres, a small world orbiting where a much larger planet might have been expected. Soon, Pallas, Juno, and Vesta were found, more small bodies in that zone. At first, Ceres was called a planet, but as dozens more of these objects were detected, it became clear that Ceres was the largest of a whole belt of minor planets, not a lone new world on par with the others. By the mid-19th century, school textbooks briefly swelled the planet count to as high as 11, only to drop back down as Ceres and its kin were reclassified as a separate category. The word planet came to be reserved for the major bodies that dominated their orbits. By the turn of the 20th century, the solar system's 8 primary planets were well known, but some astronomers suspected there might be yet another planet lurking beyond Neptune, Planet X, as it was dubbed. Percival Lowell, an American astronomer, hunted for this theoretical planet in the early 1900s, driven by hints of irregularities in Neptune's motion. Lowell did not find it, but after his death, the search continued at Lowell Observatory in Arizona. In 1930, a young astronomer named Clyde Tombaugh systematically photographed the star fields of the ecliptic and painstakingly looked for anything that moved. On a cold February day, Tombaugh found a dim speck that shifted position against the stars. It was the long-sought Planet X, soon named Pluto, after the Roman god of the underworld. The public was enthralled. Pluto was hailed as the 9th planet, a tiny, distant oddball in the solar system's outer reaches. For much of the 20th century, the solar system was taught as 9 planets, Mercury through Pluto. But as telescopes improved, especially towards century's end, we began to find more objects orbiting out near Pluto. In 1992, the first of many Kuiper Belt objects was discovered not far from Pluto's orbit, implying Pluto was not a lone maverick, but part of a larger population of small, icy worlds. The trickle of discoveries became a deluge in the 2000s. Then, in 2005, astronomers announced Eris, an object about as large as Pluto, far beyond Pluto's orbit. Suddenly, our neat conception of the solar system was challenged. If Pluto was a planet, why not Eris? And what about the other large Kuiper Belt objects like Makemake and Haumea being found? The field reached a crossroads. In 2006, the International Astronomical Union took a vote in a meeting that echoed around the world. They formally defined the term planet for the first time. According to the IAU, a planet must orbit the Sun, be massive enough for its gravity to pull it into a nearly round shape, and have cleared the neighborhood around its orbit. By that definition, Pluto failed the third criterion, since it shares the outer solar system with many similar icy objects. Pluto was reclassified as a dwarf planet along with Eris and Ceres. Overnight, the solar system went from 9 planets to 8. The decision was contentious. Many in the public lamented the demotion of Pluto, and even some astronomers disagreed, pointing out that Earth, Jupiter, and others still have small neighbors in their orbits. The debate over what constitutes a planet continues philosophically, but in practice, the new terminology stuck. We now speak of the 8 classical planets and a growing menagerie of dwarf planets. This historical journey, from the earliest recognition of wandering stars, to the Copernican revolution that made Earth a planet, to the telescopic discoveries of new planets, and finally to the reclassification of Pluto, shows how our understanding of planets has evolved with our knowledge. We moved from an Earth-centered universe to a Sun-centered solar system, and then to a vision of countless solar systems in our galaxy. Each step required us to redefine our place in the cosmos, and even as we debated definitions, we learned that nature resists rigid categories. Planets come in a continuum of sizes and orbits. The line between planet and not planet can be blurry at the edges. The story of how we came to know the planets is a story of curiosity, persistence, and a willingness to change our perspective when confronted with new evidence. Having placed ourselves among the planets and traced their discovery, we now turn to explore the planets themselves as worlds. We begin with the inner solar system, those rocky neighbors of Earth that bask closest to the Sun's fire. The inner worlds: Mercury, Venus, Earth, and Mars. We begin our planetary journey with the inner solar system, a realm of sun, baked rocks, and metal. These are the terrestrial planets, small, dense, and composed mostly of silicate rock and iron. Born of similar materials and initially not so different, they have since diverged into four dramatically distinct worlds. From airless craters to runaway hothouses to a living blue oasis and a frozen desert, the inner planets show how varied outcomes can be even among sister worlds. Mercury, the closest planet to the Sun, is a little grey furnace of extremes. It is the smallest of the four inner planets, only slightly larger than our Moon. Like the Moon, Mercury's surface is heavily cratered and ancient, recording a violent history of impacts. There are brilliant ray crater patterns splashed across its dark grey terrain and enormous basins from asteroid collisions long ago. Mercury has almost no atmosphere, just a whisper of atoms blasted off its surface by the sun's radiation, so nothing shields it from meteoroids or evens out its temperature. Daytime on Mercury is blistering, hot enough to melt lead, but the night plunges into frigid darkness since there is no substantial air to trap the heat. A Mercurian day lasts 2 Mercury years long, because Mercury rotates slowly and orbits fast. This results in oddities. If you could stand on Mercury's surface, you would see the sun blazing huge in the sky, rising and setting in a slow, drawn out dance, even briefly reversing course around sunrise due to Mercury's orbital resonance. Inside, Mercury is a world that punches above its weight. Despite being so small, it is incredibly dense, almost as dense as Earth, because it contains a gigantic iron core occupying most of its interior. This core, spanning about 3/4 of the planet's diameter, generates a magnetic field around Mercury, albeit a feeble one only about 1% as strong as Earth's. Still, it's remarkable that this tiny, slowly rotating planet maintains any magnetic field at all. Mercury's iron heart also hints at a dramatic birth. Perhaps it formed from normal proportions of rock and metal. But a titanic impact early on stripped much of its rocky mantle away, leaving a metal, rich remnant. On Mercury's surface, the evidence of an active past includes long scarps and cliffs, some hundreds of kilometers long and soaring up to a mile high, that crisscross the terrain. These formed as Mercury's core and mantle cooled and contracted, wrinkling the crust above. Volcanic plains, now solidified, also exist, indicating that billions of years ago, lava once flowed across Mercury's surface. But for at least the last few billion years, Mercury has been geologically quiet, a bare, inert world of extremes. It is a planet essentially without air or water, where the landscape is carved only by impact and the slow thermal cracking of sun-baked rocks. In the brilliant morning sun, the ground would be blinding and dead silent, and at night, the stars would burn cold in a black sky over a landscape as still as a tomb. Leaving little Mercury and moving outward, we encounter Venus, often called Earth's twin in size and composition, but in reality, a twisted mirror image of Earth, similar in bulk, yet utterly hellish in condition. Venus is almost exactly the same size as Earth and formed in the same neighborhood of the Sun, presumably with similar ingredients. It likely started out much like Earth, with volcanoes, a thick atmosphere, and possibly even oceans. But at some point, Venus took a divergent path and fell victim to a runaway greenhouse effect. Today, Venus is a world enshrouded in dense, yellowish cloud, its surface hidden from view in visible light. That thick atmosphere is composed overwhelmingly of carbon dioxide, with clouds of corrosive sulfuric acid droplets whipping around the planet. The weight of Venus's atmosphere is enormous. At the surface, the pressure is about 92 times that of Earth's sea level. This heavy blanket has trapped so much heat that Venus's surface is the hottest in the solar system, around 464 degrees Celsius everywhere, day or night, pole or equator. It is hotter even than Mercury, despite being nearly twice as far from the Sun, solely because of the greenhouse gases that lock in the Sun's heat. In essence, Venus shows what happens when a planet's heat balance goes awry. Sunlight passes through the clouds, heats the surface, and the infrared heat cannot escape efficiently due to the CO2, causing a feedback loop of warming. Long ago, Venus might have had temperate conditions, but as the sun grew brighter over eons, Venus's oceans likely evaporated, and water vapor helped drive temperatures up until the ground itself baked out carbon dioxide from rocks, filling the air with CO2 and turning the planet into a pressure cooker. If you could descend through Venus's clouds, you would find the light growing dim and orange, tinted by the sulfuric haze. By the time you reached the ground, it would be twilight at midday, and the air would be a toxic yellowish fog, so thick it feels almost like a fluid. The heat would be instantly overwhelming, high enough to melt lead, and certainly high enough to melt any lander electronics within an hour or two. The landscape, as revealed by Soviet Venera landers and radar mapping from orbit, is a rolling desert of orange, red rocks, and vast volcanic plains. Venus's surface has mountains higher than Everest and great plateaus, as well as thousands of volcanoes, from huge shield volcanoes to innumerable small cones. The terrain has strange features called coronae, circular patterns hundreds of kilometers wide, believed to be caused by upwellings of magma pushing on the crust. Yet surprisingly, there are few impact craters. The relative lack of craters tells us Venus's surface is geologically young, maybe only 500 million years old. Planetary scientists suspect that Venus underwent a global resurfacing event, perhaps massive volcanism that paved over older terrain, and it may still be volcanically active today. In fact, recent studies of old radar images have shown hints of change in some calderas, suggesting an ongoing eruption, and the Venusian atmosphere contains mysterious chemistry hinting at active volcanoes. However, Venus has no plate tectonics like Earth. Its crust appears to be one giant stagnant lid, which might periodically break down in outbursts of planet-wide volcanism, essentially repaving the planet in floods of lava. Beneath the surface, Venus likely has a metallic core and a mantle similar to Earth's, but unlike Earth, it spins extremely slowly. A Venusian day is 243 Earth days, and curiously, it spins backwards. This sluggish rotation is likely one reason Venus has almost no magnetic field. Without a protective magnetosphere, the upper atmosphere of Venus is constantly bombarded by the solar wind, which slowly strips away lighter molecules. Yet the atmosphere is so thick and heavy that losing some particles to space hardly dents it. Standing on Venus, you would experience a bizarre scene, a dim orange glow in all directions through the haze, the air utterly still near the ground, and a forbidding, silent landscape of rocks and gently sloping volcanic plains. It is an infernal environment, the closest thing to a vision of hell on any planet, and a stark warning of the power of atmospheric chemistry gone wrong. Traveling onward, we arrive at our own planet, Earth. It might seem unnecessary to describe Earth among its neighbors, but viewing Earth as a planet, one of many, is key to understanding what makes it special. Earth is the only planet we know of that hosts life, and not just a few microbes, but a rich biosphere of complexity and diversity, including us, who can marvel at that fact. Several factors conspire to make Earth a haven amid the void. It orbits in the habitable zone of the Sun, where temperatures allow liquid water to persist on the surface. Our planet is just large enough to hold on to a substantial atmosphere, but not so large as to become a gaseous giant. Earth's surface is a mosaic of blue oceans, green and brown continents, and white clouds, a dynamic, ever-changing patchwork, sculpted by both geological forces and living organisms. Unlike the rest of the inner planets, Earth's crust is divided into moving plates, an evolving jigsaw puzzle riding atop the slow churning of the mantle. This plate tectonics is a geological wonder. Continents drift, collide, and separate. Earthquakes rumble along faults. Volcanoes emerge where plates diverge or converge. Over millions of years, this process rejuvenates the surface, builds mountains, and recycles carbon, and may be crucial in regulating Earth's climate over geologic time. Indeed, plate tectonics, with its ability to bury carbon, rich sediments, and then release CO2 via volcanoes, acts as Earth's thermostat, keeping temperatures within a range that allowed oceans to remain liquid for billions of years. Earth's atmosphere is a unique mix: 78% nitrogen, 21% oxygen, plus traces of other gases like argon, carbon dioxide, and water vapor. That oxygen is a direct product of life. Photosynthetic organisms have been exhaling it for eons. The atmosphere is dense enough to buffer the surface from small meteoroids and to distribute heat around the globe, but thin enough that our planet isn't smothered in crushing pressure. It gives us a mild greenhouse effect, enough to keep the oceans from freezing solid, but not a runaway like Venus. And it shields us from deadly solar and cosmic radiation, especially thanks to Earth's magnetic field. Generated by a rotating, convecting liquid iron core, our magnetic field forms a protective bubble that deflects charged particles from the Sun. Where some of those particles do leak through near the poles, Earth offers a dazzling light show, the auroras shimmering green and red in polar skies. Earth's magnetic field, plate tectonics, and moderate atmosphere all work in concert with the Sun's favorable distance to create a stable, life-friendly environment. In that stable environment, water could remain liquid and life could take hold. Life, in turn, transformed the surface and air, covering once barren rock with soil and foliage, and pumping out oxygen to create an ozone layer protecting the surface from ultraviolet rays. From space, Earth is a shimmering blue marble with swirling white weather systems, a striking contrast to the monotonous clouds of Venus or the rust, red dust of Mars. Yet, early in its history, Earth might have looked more like those worlds in some ways. The young Earth's atmosphere had no oxygen and was rich in carbon dioxide and methane. The surface was largely molten at first and heavily bombarded by asteroids, pockmarking it like Mercury. But Earth cooled, oceans formed, life arose, and life's presence terraformed the planet into the benign paradise we now cherish. Earth's geology and biology are deeply intertwined. It is the only planet known where rocks breathe and living creatures move mountains. While Earth has its share of extreme environments, from Antarctica's icy wastes to the Sahara's furnace sands, it remains the gentlest of the inner planets, blessed with liquid water and a breathable sky. It is, simply put, home. And as we study the other planets, we constantly hold Earth as the reference, asking, why is this planet dead or boiling while Earth thrives? The answers inform our understanding of climate, habitability, and the delicate balance that makes our world livable. Stepping away from Earth, we venture back into harsher realms. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life, or at least as a world most similar to our own. It is often called the Red Planet for its reddish-orange hue when seen in the sky, a color due to iron oxide dust coating much of its surface. Mars is about half Earth's diameter and only 1/10 its mass, a modest world that has undergone dramatic change over time. Today, Mars is a cold, dry desert planet. Its atmosphere is a thin envelope of carbon dioxide at less than 1% the pressure of Earth's, essentially a tenuous sky that offers little insulation or protection. Daytime temperatures on Mars near the equator in summer might rise to a balmy 20 degrees Celsius, but at night they plummet far below freezing. At the poles in winter, carbon dioxide from the air freezes directly onto the surface as dry ice, forming seasonal polar caps that sublimate when spring returns. This leads to large seasonal pressure swings and even causes the atmosphere to shift mass between hemispheres, driving global winds. Mars wasn't always so barren. Ancient Mars was more Earth, like all the evidence we've gathered from orbiters, landers, and rovers tells us that billions of years ago, Mars had liquid water flowing on its surface. NASA's rovers have driven through dry riverbeds and studied layered rocks that formed in long, vanished lakes. We have seen branching valley networks etched into the highlands, immense outflow channels gouged by catastrophic floods, and mineral deposits that only form in the presence of water. Mars today has water too, but it's mostly locked up as ice in the polar caps or underground, and a tiny amount as vapor in the atmosphere. What happened? Mars's grip on its atmosphere weakened over time. Being smaller, Mars lost heat faster than Earth. Its once molten core partially solidified, and the global magnetic field that might have existed early on dwindled away. Without a strong magnetosphere, the solar wind gradually stripped off the atmosphere. Air pressure fell, temperatures dropped, and surface water either froze or escaped into space. Volcanoes on Mars likely vented gas and lava for a time, perhaps providing temporary warmth, but volcanic activity too has waned. The youngest lava flows on Mars are tens of millions of years old, and no eruptions have been observed in modern times. Still, Mars is not entirely static. It has weather. Thin as it is, the atmosphere can stir up winds that raise reddish dust into towering dust devils that dance across the plains, and occasionally into planet-wide dust storms that can shroud the entire globe in haze for weeks. Its sky often has a butterscotch hue due to fine dust suspended in the air. Wispy clouds of water ice occasionally appear, and at dawn and dusk they can catch the sunlight, creating delicate pastel streaks in the Martian sky. Mars also has seasons, similar in cause to Earth's. In spring and summer, the polar CO2 ice caps partially evaporate, exposing underlying water ice. In winter, they grow as CO2 snow falls. On a Martian summer day, you might see frost that formed overnight glinting in the morning sun, or even a hazy, localized dust cloud that could be analogized to a Martian rainstorm of dust. The Martian surface is a study in contrasts. There are immense shield volcanoes on the Tharsis Bulge that dwarf any on Earth. Just off Tharsis lies Valles Marineris, a canyon system so vast it would stretch across the entire United States, up to 4,000 kilometers long, 200 kilometers wide, and 7 kilometers deep. This Grand Canyon of Mars likely started as a tectonic crack when Tharsis uplifted, then was widened by landslides and perhaps erosion. Elsewhere, the northern hemisphere of Mars consists mostly of rolling, lower plains, whereas the southern hemisphere is high, cratered highlands, an indication that something created a dichotomy in Mars's crust ages ago. Scattered across Mars are impact craters of all sizes, some hosting dune fields within them, others showing gullies on their walls that hint at past flows of water or CO2 ice. Unlike the Moon or Mercury, however, Mars's craters often look worn down, softened by wind, blown dust, or perhaps by ice action. There are also curious features, like the mysterious recurring slope lineae, dark streaks on some crater and canyon walls that grow in warm seasons and fade in cold, once thought to be brine flows. Despite its harshness, Mars remains the most potentially habitable planet after Earth. It is cold, but not beyond the tolerance of life. In fact, hardy microbes on Earth survive in Antarctic ice and dry valleys that resemble Mars. It has water ice in abundance, and perhaps liquid water brines occasionally trickling just beneath the surface. In recent years, tantalizing detections of methane in Mars's atmosphere have stirred excitement, since methane can be a byproduct of microbial life. The dream of life on Mars is one of the reasons we have sent so many probes there. From the Viking landers in the 1970s to the latest Perseverance rover drilling samples for a future return to Earth, we have been reading Mars's history like a book written in rock. That story appears to include a long, gone epoch of rivers and lakes, a gradual climate catastrophe, and the transformation into the cold desert we see now. Mars today is a time capsule of planetary evolution, showing us what can happen when a world's fortunes turn for the worse. Its once thick atmosphere is mostly gone. Some of it lies frozen at the poles, some in the ground, and some atoms still drift in space as a tenuous corona around the planet. In some, the inner solar system presents 4 different fates for terrestrial planets. Mercury is an airless, baked rock, a planet stripped to its core. Venus is a suffocating hothouse under perpetual clouds, a planet where the greenhouse effect ran rampant. Earth is a balanced, vibrant world, a planet just right for liquid water and life. Mars is a once potential Earth that fell into cold desolation, a planet that lost its warmth and air. These worlds teach us about volcanism, climate, and habitability by comparison. Why did only Earth end up with lush oceans and a breathable sky? The inner planets hold the clues in their craters, rocks, and atmospheres. As we leave Mars and venture beyond the asteroid belt, the sunlight fades and an entirely different kind of planet emerges. Titanic worlds of gas and ice, where swirling storms could swallow continents and rings of dust and ice trace cosmic harmonies. Let us now step into the realm of the giant planets, where extremes reach a new level and moons become worlds of their own. Giants of the outer solar system: Jupiter, Saturn, Uranus, Neptune. Passing beyond the asteroid belt, the sun's warmth diminishes and the worlds undergo a dramatic change. Here lie the giant planets, Titans composed mostly of gas and icy fluids, with no solid surface to stand on. They dwarf the rocky inner planets in size and mass. Each is like a miniature solar system unto itself, with rings and moons forming complex families. They are planets of colossal storms, deep mysteries, and delicate rings, where the simple word surface loses its usual meaning. Jupiter is the colossus of our solar system, the 5th planet from the Sun, and by far the largest. With a diameter of about 143,000 kilometers and a mass more than twice that of all the other planets combined, Jupiter looms as a great banded sphere of tan, orange, and white. Composed mostly of hydrogen and helium gas, it is often likened to a failed star. It would have needed to be about 80 times more massive to ignite fusion in its core. Instead, Jupiter shines not by its own light, but by reflecting the sun's, and by emitting a bit of heat it retains from its formation. When you gaze at Jupiter through a telescope, you see not a solid surface, but the tops of its cloud decks, organized into parallel bands that wrap around the planet's fast rotating body. Jupiter spins on its axis in just under 10 hours, an incredibly fast rotation for such a huge planet. This rapid spin flattens Jupiter slightly and drives strong jet streams that separate its cloud bands. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a titanic storm roughly 1.3 times the width of Earth that has raged for centuries like a cosmic hurricane. Its brick red clouds swirl counterclockwise in Jupiter's southern hemisphere. Though it has been shrinking in recent decades, the red spot remains an icon of planetary science, a reminder that weather on other worlds can be on a scale far beyond anything on Earth. Jupiter's entire atmosphere is dynamic. Smaller storms come and go, white ovals and brown barges drift in the cloud lanes, and lightning crackles within towering thunderheads the size of continents. Near the poles, Jupiter's Juno spacecraft has revealed clusters of cyclones arranged in geometric patterns. At the North Pole, a central cyclone is encircled by 8 others like a flower of storms, all enduring and maintaining a surprisingly stable configuration. At the cloud tops, the temperature is around 45 degrees, but it grows hotter and denser as you descend. There is likely no sharp surface where gas turns to liquid. Rather, As pressure increases, hydrogen gas gradually becomes a supercritical fluid, and then a weird metallic form in Jupiter's depths. Beneath the storms, Jupiter hides more wonders. Its immense gravity compresses its interior to extreme pressures. Deep down, the hydrogen is squeezed into a state where it conducts electricity like a metal. This metallic hydrogen region, rotating rapidly, is believed to generate Jupiter's powerful magnetic field, the strongest of any planet, with a magnetosphere that extends millions of kilometers and envelops Jupiter's moons. This magnetic field traps charged particles and produces intense radiation belts. It also powers brilliant auroras at Jupiter's poles, glowing in ultraviolet and infrared, far larger and more energetic than Earth's. The interplay of Io's volcanoes and Jupiter's magnetosphere even creates a permanent flow of electric current between them and fills Jupiter's environment with sulfur and oxygen ions that contribute to auroras and radio bursts. Surrounding Jupiter is a retinue of moons, more than 90 known at last count, ranging from tiny asteroid-like rocks to planet-sized spheres. The four largest, the Galilean moons, were first seen by Galileo in 1610 and remain some of the most remarkable places in the solar system. Closest to Jupiter orbits Io, a tortured volcanic world. Io is the most volcanically active body in the solar system. Its interior flexed and heated by Jupiter's gravity. Its surface is mottled with sulfurous yellows and oranges, and dotted with erupting volcanoes that spew fountains of lava and giant plumes of sulfurous gas that can rise 300 kilometers high. Next out is Europa, a smooth, icy moon slightly smaller than Earth's moon. Europa's surface is crisscrossed with reddish-brown cracks and ridges over a bright white shell of water ice. Almost no craters mar Europa. It's young and active. Beneath that ice, scientists are confident lies a global ocean of liquid water, kept fluid by tidal heating. Europa's hidden ocean, perhaps 100 kilometers deep under an ice crust a few to 30 kilometers thick, makes it one of the prime candidates in the search for extraterrestrial life. Beyond Europa comes Ganymede, the largest moon in the solar system. Ganymede is a frozen world with a mix of old, dark cratered regions and somewhat younger, lighter grooved terrain from past tectonic activity. It even has its own internally generated magnetic field, the only moon known to have one, hinting at a molten iron core within. And then Callisto, the outermost Galilean moon, an ancient cratered ball of ice and rock that appears to have changed little in 4 billion years. Callisto's surface is saturated with impact scars, a record of the early solar system's heavy bombardment. While not as flashy as Io or Europa, even quiet Callisto might harbor a subsurface ocean, and it has a composition like a primordial mix of rock and ice, a relic of the solar nebula. Each of these moons could warrant chapters of their own, and indeed they will come up again when we talk about habitability and exploration. For now, they underscore Jupiter's role as a mini solar system, a master planet with its own complex gravitational web, shaping the lives of its moons. Jupiter also sports a barely visible ring system, thin bands of dust encircling the planet above its cloud tops. Unlike Saturn's bright icy rings, Jupiter's rings are tenuous and were discovered only when Voyager 1 flew through Jupiter's shadow and saw them glint. The dust likely comes from meteoroid impacts on small inner moons. The rings remind us that all giant planets have rings of one form or another, a natural consequence of having many orbiting bodies and frequent collisions or ice eruptions to supply ring material. Now we move one step farther out to Saturn, the sixth planet from the Sun, often considered the most beautiful. Saturn is a gas giant like Jupiter, but slightly smaller and significantly less massive. In fact, Saturn has the lowest density of any planet, less than water, meaning if you could find a bathtub big enough, Saturn would float. Visually, Saturn is stunning for one reason above all: its rings. Saturn's rings form a broad, flat disk encircling the planet's equator, composed of countless icy particles ranging in size from dust grains to boulders. They sparkle in the sunlight and are divided into several major rings separated by gaps. From Earth, even a small telescope shows Saturn's rings as a separate structure. Up close, they resolve into myriad ringlets, ripples, and braids sculpted by gravitational interactions with Saturn's moons. The rings are extremely thin, only tens of meters thick in most places, despite spanning over 250,000 kilometers in diameter. They are likely relatively young and are slowly evolving. Saturn's gravity is pulling ring material inward, which means the rings may gradually thin out over tens of millions of years. For now, however, they are a breathtaking demonstration of cosmic geometry and physics. A disk of ice grains tracing the invisible lines of Saturn's gravity and rotational balance. Saturn itself, beneath the rings, is often seen as a pale golden globe banded by subtle belts and zones like Jupiter's, but far more muted in color. Its upper clouds are composed of ammonia crystals. Deeper down likely lie clouds of ammonium hydrosulfide and water, but these are hidden beneath hazes. Saturn's atmosphere is colder than Jupiter's, and its weather, while not as vividly colored, can still be violent. Roughly once per Saturnian year, Saturn experiences a great white spot, an enormous storm that erupts and encircles the planet. One such storm was observed by Cassini in 2011. It began as a brilliant white cloud in the northern mid-latitudes and spread into a band that wrapped around Saturn, accompanied by lightning and turbulent swirls the size of Earth, before dissipating. Saturn also exhibits a bizarre phenomenon at its north pole, a long-lived hexagonal jet stream pattern, first noticed by Voyager and later seen in detail by Cassini. This six-sided wave, like flow of clouds, each side longer than Earth's diameter, rotates as a unit around the pole. At the center of the hexagon sits a whirling hurricane, like vortex with an eye several thousand kilometers across. Why Saturn's atmosphere naturally forms a hexagon is still debated. Likely it's a result of a standing wave in the fluid dynamics of its atmosphere at that latitude. Like Jupiter, Saturn radiates more heat than it receives from the Sun, though the mechanism is different. Saturn appears to be undergoing helium rain as the planet cools. Helium condenses out of the hydrogen, helium mixture in the upper layers and falls inward, releasing gravitational energy as heat. This helps drive Saturn's weather from below. Saturn's magnetic field is strong. Uniquely, Saturn's magnetic field is almost perfectly aligned with its rotation axis, a fact that challenges dynamo theories. Nevertheless, Saturn has bright auroras observed at ultraviolet wavelengths, and its strong field traps some radiation. Saturn's family of moons is rich and varied, more than 80 known moons. The largest, Triton, is one of the most intriguing objects in the solar system. Triton is bigger than Mercury and enveloped in a thick orange haze of atmosphere. In fact, Triton is the second largest moon and the only moon with a substantial atmosphere, even denser at the surface than Earth's, composed mainly of nitrogen with a few % methane. For a long time, that smog hid Triton's surface completely. But the Cassini mission's radar and the Huygens lander unveiled a world surprisingly Earth-like in some ways. Triton has rivers, lakes and rain, but of liquid methane and ethane instead of water. At Triton's frigid surface temperature of 179 degrees, water is as hard as rock, and hydrocarbons take the role of the water cycle. Dark methane seas dot Triton's polar regions, complete with shoreline features, islands, and possibly waves. There are branching river channels carved by methane rain flowing into valley networks, and extensive equatorial dune fields made of exotic organic sand. Standing on Triton, you would see an orange-colored sky and a dim sun. The air pressure is about 1.5 times Earth's. You could almost fly by flapping wings strapped to your arms, given Triton's dense air and low gravity. It is an alien yet eerily familiar landscape. In fact, perhaps the most Earth-like place in the solar system, aside from Earth itself, albeit at cryogenic temperature and with a completely different chemistry. Titan likely has a subsurface water ocean as well, beneath the ice crust, making it a double world of interest. A possible haven for some form of life in the warm water below, and a laboratory for prebiotic chemistry in the organic, rich surface environment. Another of Saturn's moons has seized our attention, Enceladus, a small ice moon only about 500 kilometers across. Enceladus looks like a shiny white snowball, reflecting almost all sunlight. For years, its smooth, bright surface hinted something was renewing it. The Cassini spacecraft confirmed that in spectacular fashion. It discovered active water geysers erupting from Enceladus's south pole. Dozens of icy jets spray water vapor and tiny ice particles continuously into space, feeding Saturn's faint E-ring and indicating a subsurface ocean of liquid water beneath Enceladus's fractured crust. Cassini even flew through the plumes and detected salts, organics, and tiny grains of silica. In other words, Enceladus has nearly all the ingredients for life: water, heat, and organic molecules, and it's ejecting them into space, begging for further exploration. The surface around the South Pole has tiger-stripe fissures that are warm and flexing with tidal pulls from Saturn, essentially cryovolcanic vents. This little moon, with a global ocean about 30 kilometers distance below an ice shell some 20 kilometers thick, has become one of the prime targets in the search for extraterrestrial life. Saturn's other moons offer delights as well. Iapetus, half of its surface bright as snow and the other half dark as coal, with a unique equatorial ridge that makes it look like a walnut. Rhea, Tethys, and Dione, medium-sized moons, heavily cratered and cut by ancient canyons. Dione might hide a subsurface ocean too. Mimas, with its giant crater, Herschel giving it a Death Star appearance. Phoebe, a retrograde irregular moon perhaps captured from the outer solar system, rich in primitive material. Each moon tells a different chapter of Saturn's story, from formation to capture to geologic evolution. Yet, through it all, Saturn's majestic rings cast their shimmering veil, illuminating the night sides of moons and casting shadows that stripe Saturn's own cloud tops in eclipse season. Beyond Saturn, the sunlight becomes faint. We reach the ice giants, Uranus and Neptune, the 7th and 8th planets. They are called ice giants, not because they are made of solid ice, but because in addition to hydrogen and helium, they contain a higher proportion of ices, water, ammonia, methane, in a hot, slushy, fluid state inside. Uranus orbits about 2.9 billion kilometers from the Sun, taking 84 years to complete one orbit. It's a pale blue-green orb, about 4 times Earth's diameter, and notably tilted over on its side. Uranus's axial tilt is 98 degrees, meaning it practically rolls around the Sun like a ball. This bizarre orientation is likely due to a colossal collision with a protoplanet long ago. The consequence is extreme seasons. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. When Voyager 2 flew by in 1986, it was southern summer, and Uranus's south pole faced the Sun almost directly. Voyager saw a virtually featureless sphere, a smooth cyan disk with only the faintest hints of cloud, bands or spots. Uranus looked like a painted marble, leading many to call it bland. But as Uranus approached its equinox in 2007, Earth-based telescopes and Hubble started seeing signs of weather: bright white cloud caps, dark spots, and streaky clouds. Uranus, it turns out, has a dynamic atmosphere that awakens when the Sun's heating is distributed more evenly. During the 2010s, astronomers observed some storms with ferocity comparable to Neptune's, including one huge storm in 2014 that was surprising given how far from the Sun Uranus is. Most of the time, though, Uranus is tranquil, looking, with gentle banding visible in enhanced images, and a serene aquamarine hue due to methane in its atmosphere, absorbing red light and reflecting blue, green. At cloud tops, Uranus is a frigid 215 degrees Celsius. Uranus also comes with rings and moons. It has a set of thin, dark rings made of radiation, darkened ice, and dust. They are narrow, kept in line by shepherd moons, and not nearly as showy as Saturn's, but they form a delicate series of hoops around the sideways planet. Uranus's moons include Titania, Oberon, Ariel, Umbriel, and Miranda. They are icy, cratered worlds, a few showing evidence of past internal activity. Miranda, for instance, displays one of the strangest surfaces in the solar system, patchwork regions of ridges and valleys next to older cratered terrain, and a cliff estimated at 20 kilometers high, a fall from which would take 15 minutes in Miranda's weak gravity. It's as if Miranda was shattered and reassembled or underwent partial melting that froze in bizarre patterns. The larger moons have lesser quirks. Ariel has relatively few craters and signs of youthful resurfacing. Titania has giant canyons. Uranus's moons, like the planet, roll on their sides as they orbit which means, at solstices, one hemisphere of each moon is in continuous sunlight and the other in darkness. What seasonal effects that might cause on those frigid surfaces, we don't really know yet. Neptune, the eighth planet, orbits about 4.5 billion kilometers from the Sun, taking 165 years for one circuit. It's very similar to Uranus in size and composition, but Neptune is notably more active and more intense in color, a deep azure blue. Discovered in 1846 by mathematical prediction, Neptune was visited by Voyager 2 in 1989. Voyager 2 found a dynamic atmosphere, a great dark spot in the southern hemisphere, and bright white clouds zipping around. Neptune's winds are the fastest in the solar system, up to 2,100 km/h, especially around those dark oval storms. The great dark spot seen in 1989 was a large high-pressure system exposing darker gases below, roughly the size of Earth, and it vanished a few years later. But other dark spots have since appeared and faded on Neptune. Unlike Jupiter's huge stable spot, Neptune's seem to be shorter, lived storms that come and go every decade or so. Neptune's upper atmosphere is about 200 degrees. Intriguingly, Neptune, like Jupiter and Saturn, radiates about 2.6 times more heat than it gets from the Sun, likely due to residual heat from formation. This internal energy might help drive the vigorous weather we see. Neptune's seasons last over 40 years. We haven't observed a full Neptunian season change yet, but in the decades since 1989 to the 2020s, we've seen some puzzling climate changes. The global temperature in Neptune's stratosphere actually dropped by about 7 degrees Celsius from 2003 to 2018. Then the South Pole suddenly warmed by 11 degrees from 2018 to 2020. It's a reminder that these far-off atmospheres can have variability we don't fully grasp yet. Neptune, too, has rings and moons. It sports faint rings with clumpy arcs. The outer Adam's ring has segments named Liberty, Equality, and Fraternity, where dust is clustered, for reasons initially mysterious until moonlets were found that shepherd those arcs. And Neptune's moon's number 14 at last count. The standout is Triton, Neptune's largest moon, which orbits backward relative to Neptune's rotation. Triton is a captured Kuiper belt object, likely snared by Neptune's gravity long ago. Triton is an ice world almost as big as our moon, with a young surface of frozen nitrogen, water ice, and weird cantaloupe terrain, and it is geologically active. Voyager 2 saw geysers on Triton, dark plumes of nitrogen gas and dust spraying up from the surface, carried by winds before falling. These are essentially cryovolcanoes driven by seasonal heating of Triton's south polar cap. Triton's thin atmosphere is about 1/70,000th Earth's pressure, but enough to have winds that bent those geyser plumes. Triton is extremely cold, yet it still has this slight atmosphere and active geysers, an astounding find. Triton likely has a subsurface ocean as well, kept liquid by residual internal heat or past tidal heating. Because of its retrograde orbit, Triton is slowly spiraling inward toward Neptune. Billions of years from now, it may either break apart into a spectacular ring or crash into Neptune. Neptune's other moons are much smaller and ice, rocky. Nereid has an extremely elongated orbit. Proteus is the second, largest, but still irregularly shaped. It's as large as an object can get without its gravity crushing it into a sphere. Proteus, dark and heavily cratered, might have avoided melting into a sphere by forming late, after the solar system calmed down. Tiny Hydra and Naiad and others zip around Neptune in closer orbits, some in complex resonant dances. Neptune's moon system likely lost whatever original satellites it had during Triton's capture. What we see now are either captured asteroids, comets, or fragments of an ancient moon system reassembled in new orbits. Thus, the outer solar system presents grandeur quite different from the inner. Here we have giant globes of gas and ice, lacking solid surfaces, but adorned with storms larger than Earth and delicate rings. We have an array of moons that are worlds in their own right, some sterile and cratered, others with subsurface oceans or thick atmospheres or erupting geysers. The giant planets act as architects and guardians of the solar system. Their gravity shaped the orbits of countless smaller bodies and may have steered water, rich comets toward the inner planets, possibly delivering Earth's oceans. Jupiter, especially, has shielded the inner solar system at times by vacuuming up comets, though it can also fling asteroids our way if they get too close. The giants likely migrated early on, scattering the debris disk and causing the late heavy bombardment that peppered the inner worlds with craters, and perhaps ejecting leftover planetesimals to form the distant Oort cloud of comets. As we leave Neptune behind, we pass into the realm of icy debris, the Kuiper Belt and beyond, where the sun's influence wanes. Yet even here we find worlds of consequence, the dwarf planets, which challenge how we define planethood and carry clues to the solar system's origin. Dwarf planets, worlds at the edge, and the definition of planethood. Far beyond Neptune's orbit, the solar system continues into a vast realm of icy bodies. Here, in the dim frontier, lies the Kuiper Belt, a broad ring of frozen remnants from the solar system's formation. Among these are several worlds large enough to be round, worlds that in another context might have been called planets. In fact, one of them was long honored as the 9th planet, Pluto. Today, we classify Pluto and similar bodies as dwarf planets, a category born from the realization that our cosmic neighborhood has more planets than we once thought, and that not all planets are equal in their orbital status. These distant dwarfs are small in size but rich in diversity, and they have forced us to confront the question, what does it truly mean to be a planet? Let us begin with Pluto, the iconic dwarf planet and former 9th planet. Discovered in 1930, Pluto orbits roughly 5.9 billion kilometers from the Sun on average, on a path that is highly inclined and elliptical. For 76 years, it was counted as the outermost planet, depicted as an icy oddball, until the early 21st century brought a paradigm shift. Pluto is about 2,377 kilometers in diameter, less than 20% of Earth's diameter, smaller than our Moon. But what it lacks in size, Pluto makes up for in personality. In 2015, NASA's New Horizons spacecraft flew past Pluto and revealed an astonishingly complex world. Far from a simple cratered ice ball, Pluto displays a mosaic of terrains. Towering water, ice mountains rising 4,006 kilometers high, vast smooth plains of nitrogen ice with no craters, and dark reddish regions rich in organic molecules processed by sunlight. The most famous feature is Tombor Regio, nicknamed the heart of Pluto, a bright, heart-shaped area dominating one hemisphere. The left lobe of this heart, Sputnik Planitia, is a 1,000 km wide basin filled with nitrogen, carbon monoxide, and methane ices. This frozen plain is segmented into polygonal cells, evidence of convection. Pluto's interior heat causes the nitrogen ice to slowly overturn like a lava lamp, erasing craters and renewing the surface. It's a bit mind-boggling. Here is a tiny world at the solar system's edge, with active geology powered perhaps by the slow cooling of an internal ocean, or by exotic forms of heat transfer in the ice. Pluto's thin atmosphere is another surprise. When near perihelion, its surface ices sublimate, forming a tenuous atmosphere of nitrogen with a touch of methane. This atmosphere is about 100,000 times thinner than Earth's, but enough to form layers of delicate blue haze, as imaged by New Horizons when it looked back at Pluto, eclipsing the distant sun. In Pluto's sky, the sun is just a brilliant star, but it still drives a faint weather cycle. As Pluto recedes from the sun, its atmosphere can partially freeze out onto the surface. New Horizons saw that Pluto's skies are layered with haze up to 200 kilometers altitude, and that the atmosphere is slowly escaping to space, forming a tail like a comet's. Standing on Pluto, you'd see a dim daylight with a charcoal-colored landscape, low gravity, and if you looked up, a thin bluish glow around the horizon from the atmospheric haze. Pluto doesn't wander alone. It has a system of 5 moons. The largest, Charon, is so big that Pluto and Charon orbit each other around a point in space between them. Charon itself is a fascinating world. New Horizons showed it has a rugged surface with a massive equatorial canyon system far longer and deeper than the Grand Canyon, and a strangely bi-colored complexion. The northern polar region of Charon is reddish, likely stained by gases that escaped Pluto and froze onto Charon, then were altered by solar radiation into reddish tholins. The mutual orbit of Pluto and Charon is tidally locked. Each keeps the same face toward the other, waltzing through space as an inseparable pair. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier and irregularly shaped, probably captured or coalesced debris from the giant impact that created the Pluto-Charon system billions of years ago. Moving outward, we find Eris, the troublemaker that precipitated Pluto's demotion. Eris was discovered in 2005 by a team led by Mike Brown. It's an object currently slightly smaller in diameter than Pluto, but more massive by about 25%. Eris orbits the Sun on a highly eccentric path. When found, Eris was hailed in the media as the 10th planet, but its existence underscored that Pluto was not unique. Astronomers suspected many Pluto-sized objects awaited discovery. Eris was named after the Greek goddess of discord, fitting for the chaos it introduced into our understanding. It has one known moon, Dysnomia. Eris's surface is extremely bright. Its great distance means Eris is in deep freeze. If it comes closer, it might develop a thin atmosphere like Pluto's that refreezes when far out. Eris's discovery forced the IAU to formalize the definition of planet, and under that definition, Eris joined Pluto as a dwarf planet. But in terms of geology and interest, Eris is very much a planet, like world, simply one of a vast collection in the Kuiper belt. Besides Pluto and Eris, the IAU has so far recognized 3 other dwarf planets: Ceres, Haumea, and Makemake. Ceres is unique as the only dwarf planet located in the inner solar system, residing in the asteroid belt between Mars and Jupiter. In fact, Ceres was the first dwarf planet discovered and initially considered a planet until many more asteroids were found. Ceres is about 940 kilometers in diameter, roughly the size of Texas, and contains about a third of the mass of the entire asteroid belt. NASA's Dawn orbiter visited Ceres in 2015 and unveiled a cratered world that, while much smaller than Pluto or Eris, still shows signs of internal complexity. Most famously, Dawn spotted mysterious bright spots on Ceres, particularly in the crater Ocata. These bright patches turned out to be deposits of salts left behind by briny water that erupted or seeped to the surface, essentially cryovolcanic salt flats. This indicates that Ceres, even at its modest size, had a subsurface reservoir of salty water or mud that occasionally breaches the surface as a kind of ice volcano. One such cryovolcano on Ceres is Ahuna Mons, a solitary mountain likely formed by the extrusion of viscous, icy material that then hardened. Ceres likely differentiated into a rocky core and icy mantle. It may even hold a remnant subsurface ocean or pockets of liquid. Though cold and airless, Ceres surprises us by being a kind of geological bridge between the rocky inner worlds and the icy outer worlds. Back to the Kuiper belt, Makemake is another dwarf planet, slightly smaller than Pluto. Discovered in 2005, Makemake orbits at about 45 AU on a mildly tilted orbit. It has a very high reflectivity as well, with a surface of methane and ethane ices that give it a red-brown color. For a long time, Makemake was thought moonless, but in 2016, a tiny moon was found in Hubble images. Knowing its moon will allow us to determine Makemake's mass and density. Makemake has no known atmosphere, and its average surface temperature is around 240 degrees Celsius. Then there is Haumea, one of the strangest known dwarf planets. Discovered in 2004 and officially named in 2008 after the Hawaiian goddess of childbirth, Haumea is not spherical but rather ellipsoidal due to its incredibly rapid rotation. A day on Haumea is just under 4 hours. This fast spin elongated Haumea into a rugby ball shape. It's as if someone grabbed a ball of taffy and whirled it around. The centripetal force stretched it out. Haumea is also notable for its composition. It's largely water ice, with a denser core, suggesting it might be the fragment of a larger body that collided and spun up. Supporting that, Haumea has 2 moons and is associated with a swarm of smaller Kuiper belt objects that share similar orbits and water-ice spectra, likely pieces of Haumea's shattered past self. In 2017, observers caught Haumea eclipsing a star and discovered it even has a ring, a 70-km wide ring of particles around its equator, likely in the plane of its fast rotation. Haumea's existence stretched our idea of a planet, showing that something can be round-ish and orbiting the Sun, yet far from symmetric or solitary. Beyond these, dozens of other objects around the size threshold for dwarf planet likely exist. Quasar has a moon and possibly a ring of its own. Sedna lurks on an 11,000-year orbit that takes it out to nearly 1,000 AU, possibly the first known member of the inner Oort cloud. The more we look, the more we find a continuum of worlds bridging planets and comets. The dwarf planets collectively highlight the continuum of planetary sizes and the gradations in the solar system's architecture. They forced the question, where do we draw the line between planet and smaller bodies? The 2006 IAU definition drew that line based on orbital dominance. By that rule, Pluto, Eris, Haumea, Makemake, and Ceres were reclassified because they share their space with many peers, but that definition remains debated. Some planetary scientists prefer a geophysical definition. If it's round by self-gravity, call it a planet, which would make dwarf planets planet in a broader sense. Others note that even Earth hasn't entirely cleared its orbit, but Earth so overwhelmingly outweighs them that the spirit of the definition holds. The public often still refers to Pluto as a planet out of affection. In truth, terms like planet are human categories we impose on nature's spectrum. Whether we call Pluto a planet or not doesn't change Pluto itself, with its glaciers of nitrogen, atmosphere that snows out, and potential subsurface ocean. Pluto defies any notion of being a static asteroid. We've learned that these so-called dwarfs can be just as complex and geologically active as the big planets. They are worlds by any meaningful measure. The classification is mainly about how they fit into the solar system's structure. Pluto hasn't cleared its orbit because it lives in a bustling disk of other icy bodies. That tells us about where and how it formed, but it doesn't diminish its status as a fascinating world. Indeed, studying dwarf planets like Pluto and Ceres has yielded huge insights. Ceres taught us that even small bodies can differentiate and possibly harbor liquid water or mud under the surface. Pluto showed that even in the far frozen reaches, geology goes on. Exotic ices can flow and convect like glaciers, and cryovolcanoes can build mountains. These bodies are time capsules from the solar system's formation and laboratories for processes at the extremes. They and their ilk likely delivered volatiles to the larger planets. And when we consider planets around other stars, many might be more akin to these intermediate worlds than to the 8 major planets we started out with. Having completed our grand tour of the solar system, from the sun, scorched rocks, to the gas leviathans and distant ice dwarfs, we can step back and summarize. Our solar system contains a family of worlds with a common origin but wildly divergent paths. Some went dry and airless, others drowned in thick atmospheres. Some stayed warm inside, churning and resurfacing, others went cold and quiet. And around at least one modest star out of billions, one small rocky planet found a perfect balance and became alive. With this perspective, we now venture beyond the solar system to the planets that orbit distant suns. Here, we will apply what we've learned to understand how we detect these alien worlds, what types we've discovered, and what that means for the potential for life in the cosmos. Beyond our solar system, the exoplanet revolution. For thousands of years, humans wondered if the stars in the night sky had their own planets. In the last few decades, we found the answer, a resounding yes. We are living through a revolution in which exoplanets, planets around other stars, have gone from speculation to a catalogue of thousands. This discovery has expanded our concept of what a planet can be and placed our solar system in a galactic context. The first discoveries were surprising. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed exoplanets, and they were orbiting a pulsar. These were likely bizarre worlds that survived a supernova or coalesced from its aftermath. Not at all what we expected for the first planets beyond our solar system. Then, in 1995, Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star, 51 Pegasi b, a planet at least half the mass of Jupiter, but orbiting so close to its star that its year is only about 4 days. This was a hot Jupiter, a kind of planet unknown in our solar system. It forced us to realize that planetary systems can be very different from ours. Since then, a torrent of discoveries has followed. Astronomers detect exoplanets mainly by 2 methods. The radial velocity method, which measures the star's subtle wobble due to an orbiting planet's gravity, and the transit method, which measures the slight dimming of a star when a planet crosses in front of it. The Kepler Space Telescope stared at 150,000 stars and measured their brightness precisely, catching thousands of tiny dips that revealed over 2,600 confirmed exoplanets. These planets range from larger than Jupiter gas giants to smaller than Earth worlds. We learned that super-Earths and mini-Neptunes are extremely common, yet our solar system has none of those, implying our setup might be somewhat unusual. We found hot Jupiters, gas giants hugging their stars in scorchingly tight orbits, and hot Neptunes and warm Saturns, and more. We found multi-planet systems packed in close to their stars, some with planets in orbital resonances. We found circumbinary planets, planets orbiting 2 stars. We found free, floating planets by gravitational microlensing, rogue worlds that drift through the galaxy untethered to any star. And we found planets in the habitable zones of their stars, at distances where, if conditions are right, liquid water could exist on a rocky surface. One of the most exciting sets of discoveries was the TRAPPIST system. 7 Earth-sized planets orbiting a dim red dwarf star only 39 light-years away. 3 of these lie in the star's habitable zone. They are all tidally locked and crammed in a space that would fit well within Mercury's orbit. This system provides a tantalizing example of a very different kind of solar system architecture, one where a tiny star can have a retinue of Earth size worlds potentially capable of retaining atmospheres. What are their surfaces like? Could any have water or life? Future telescopes like the James Webb Space Telescope are actually beginning to probe their atmospheres by analyzing starlight that filters through during transits. Exoplanets have shown us an astounding diversity of types. Hot Jupiters, gas giants orbiting extremely close to their stars. These have atmospheric temperatures of 1,000 pounds and 2,500 excites or more. Their atmospheres are puffed up by heat. Some are losing gas under the stellar radiation. They challenged our formation models. How did such big planets get there? We think they formed farther out and then migrated inward due to interactions with the protoplanetary disk or other planets. They taught us that migration can be a common process. Super-Earths. Planets a bit larger in radius or mass than Earth. Some may be rocky, others may have thick atmospheres. They might actually span a spectrum from big rocky planets to small gas planets. Not having one in our system means we had a gap in our understanding. Now we see they might be one of the most common types in the galaxy. A super-Earth might have higher gravity and retain a thick atmosphere or oceans for billions of years. Could they be even more clement for life than Earth? Or could they all turn into gas dwarfs with puffy atmospheres that make them uninhabitable? We're trying to find out by measuring their densities. Some super-Earths like 55 Cancri E are very dense, whereas others like Kepler, 38d, appear to have low density. Ice giants and sub-Neptunes. Many systems have planets in the 2 through 4 Earth radii range, akin to scaled down versions of Neptune and Uranus. These might have thick hydrogen, helium atmospheres on a rocky/icy core. Some could be more water-rich. The line between super-Earth and sub-Neptune might be around 1.6 thousand Earth radii. Intriguingly, Kepler data showed a dip in planet frequency around that size, suggesting many planets either have significant gas envelopes or have almost none. This phenomenon, the radius gap, likely reflects how planets either stop growing early and stay rocky or accumulate enough gas to puff up. The borderline worlds might have lost some atmosphere due to stellar radiation, ending up as rocky cores. Gas giants. Plenty of Jupiter, like or Saturn, like exoplanets have been found at various distances, some close, some at Earth, like distances, some far out. A few even orbit at Jupiter, like distances from Sun, like stars, implying their systems might have distant architectures vaguely resembling ours. We found giants in eccentric orbits. Some gas giants orbit binary star systems. We've even directly imaged a few young gas giants at wide separations. Rogue planets. Gravitational microlensing surveys have hinted that there may be numerous free-floating planets, perhaps ejected from forming systems or formed in isolation. Some estimates suggested they could be as numerous as stars or more, though recent data suggests not that common for Jupiter, mass ones. Still, it implies planet formation can be a turbulent process, with some worlds flung into the galaxy to wander alone. These would have no sunlight, just faint glow from leftover heat or radioactivity. A larger rogue could retain a thick atmosphere and maybe an internal ocean kept liquid by radiogenic heat or tidal heating from a prior moon, but life on such worlds would be a stretch. Exotic worlds. Some planets are simply weird, like lava worlds such as Corot 7b or Kepler 10b. Rocky planets so close to their stars that their surfaces are likely molten on the day side, with rock vapor atmospheres and mineral clouds that rain pebbles. Or ocean worlds that might be nearly all water by mass, essentially giant versions of Europa or Enceladus that grew larger. There's the idea of carbon planets around stars with different compositions, perhaps worlds where graphite and diamonds are abundant, or surfaces of carbide rock under tar, like skies. There are also puffy planets, gas giants with anomalously large radii for their mass, like WASP 17b, which is about half Jupiter's mass, but 1.7 times its size, and planets orbiting pulsars, or extremely metal, poor stars, or white dwarfs, each situation leading to unusual characteristics. When we compare these exoplanets to our solar system, we see that our system might not be typical in some respects. The absence of a super-Earth in our solar system is a puzzle. Perhaps Jupiter's formation prevented one from coalescing by scattering material. The lack of hot Jupiters in our system is a blessing for us. It appears that giant planets that migrate can disrupt inner systems heavily, whereas ones that stay put allow inner rocky planets to remain. Our relatively circular orbits and spaced-out configuration might not be the most common outcome. Many stars have multiple super-Earths in orbits closer than Mercury's, for example. Yet, among Sun-like stars specifically, some analyses suggest systems with a giant planet at Jupiter, like distance and small inner rocky planets, could be not extremely rare either. We're still trying to figure out how special our arrangement is. The significance of discovering exoplanets is profound. We now know that planet formation is a natural part of star formation. Planets are everywhere. The galaxy likely holds tens of billions of potentially habitable rocky worlds. We've taken the concept of planet from 5 wanderers in the sky to a cosmic norm, and each type of planet we find tests our theories. How do hot Jupiters form? Likely through disk migration or interactions. Why are super-Earths so common? Perhaps many systems form multiple mid-sized cores, which either become super-Earths or mini Neptunes, depending on how much gas they capture and how fast they migrate. What about Earth-like planets? Statistical studies from Kepler suggest perhaps 20–25% of Sun-like stars have an Earth-size planet in the habitable zone. Around red dwarfs, potentially an even larger fraction have Earth-size planets in the habitable zone, as seen with TRAPPIST and others. However, red dwarfs are volatile. Their flares and long-lived activity might strip or sterilize those planets' atmospheres. The search is now shifting from finding exoplanets to characterizing them, measuring their masses and radii, detecting their atmospheres via spectroscopy, and even directly imaging some. We have detected atmospheric constituents on some exoplanets, sodium in hot Jupiter atmospheres, water vapor on some, even hints of things like titanium oxide, or possibly clouds of silicates or iron. In 2019, water vapor was detected in the atmosphere of a sub, Neptune, in its star's habitable zone, raising interest. The ultimate goal is to detect biosignatures, signs of life, in an exoplanet's atmosphere, such as oxygen or methane out of equilibrium, or other peculiar combinations that strongly suggest biology. That will require the next generation of telescopes and perhaps specialized space observatories with coronagraphs or star shades to directly see Earth, like planets next to their bright stars. The types of exoplanets we've discovered inform our quest for life. We've learned that terrestrial planets often come in families. A star might have several, some perhaps larger or smaller than Earth. We've seen that habitable zones around red dwarfs can host multiple tidally locked Earth-size worlds. Whether those can support life is an open question. Tidal locking means one side is always hot, the other cold. But if they have atmospheres or oceans, they could redistribute heat. We also consider how giant planets in a system might affect habitability. A Jupiter analog could help by diverting comets or hinder by destabilizing orbits. Our solar system's giant planets likely had a hand in delivering water, and also in preventing too many super-Earths from forming in the inner regions. In the context of habitability, the solar system offers 3 main candidates for life as we know it: Earth, Mars, and ocean moons. But none besides Earth have confirmed life. So as we look outward, we refine what conditions might be needed. Liquid water, certainly, is high on the list. A source of energy is needed. A stable environment over some billions of years might be necessary for complex life. Planets in the habitable zone of Sun, like stars, might be best situated for that. Red dwarf habitable zone planets get a lot of flares, especially in youth. Could life survive that? Possibly, if under ocean or ground, or protected by a magnetic field and thick atmosphere. We remain cautious but hopeful. The future exploration of exoplanets is accelerating. The James Webb Space Telescope is already peering into some transiting planets' atmospheres with unprecedented detail. Upcoming missions like the Nancy Grace Roman Space Telescope will use microlensing to find rogue planets and cold planets further from stars, and test technologies for direct imaging. Further down the line, proposals for missions like LUVOIR or HABEX specifically aim to directly image Earth like planets around Sun, like stars, and search their spectra for biosignatures. On the ground, extremely large telescopes coming online in the late 2020s will be able to probe smaller exoplanets and perhaps take crude spectra of super-Earth atmospheres. It's conceivable that in the coming decades we might identify a planet where life could exist, or even find hints that it does exist, such as an atmosphere out of chemical equilibrium, strongly suggestive of biological activity. As our gaze extends to the stars, we carry the lessons of our solar system with us. We now know Earth is not alone as a potentially habitable world. There may be billions of Earths in our galaxy, but we also know habitability is fragile. Climate catastrophes like what befell Venus and Mars remind us that a planet's fate can change drastically. Earth has been lucky, but we must keep it that way. Life among the stars, the quest for habitability. When we talk about habitability, we usually mean conditions suitable for liquid water and life as we know it. From our study of planets, we've identified key factors. Distance from star. The concept of the habitable zone is crucial. Not too hot, not too cold for liquid water on the surface. For our Sun, that roughly spans from just beyond Venus's orbit to just beyond Mars's. For smaller, cooler stars, the habitable zone is much closer in. For bigger, hotter stars, it's farther out, but those stars live shorter lives. Atmosphere. A planet needs an atmosphere thick enough to create pressure for liquid water and to circulate heat, but not so thick as to induce a runaway greenhouse. Too thin, and water either freezes or boils away. The composition matters too. CO2 provides warmth, but too much can cook a planet. Some gases can be toxic to life. On Earth, life itself altered the atmosphere, creating the oxygen we breathe, which in turn allowed complex life. Magnetic field. As we discussed, a magnetic field can protect a planet's atmosphere from stellar winds. Earth's field likely helped us maintain our water and air over geologic time. Mars lost its field early, and then its atmosphere eroded away largely. Venus lacks a field, but its atmosphere is so thick that even with losses, it remains dense. Around active stars, a magnetic field could be even more critical to buffer the planet from high-energy radiation and flares. Internal heat and geology. Plate tectonics appears to help regulate climate via the carbon cycle on Earth. Volcanism also releases trapped gases and replenishes the atmosphere. A geologically dead planet might end up like the Moon: no atmosphere, cold interior, and static surface, not hospitable. Mars's waning volcanism might have doomed its climate. Venus's rampant volcanism may have contributed to its runaway greenhouse by belching massive CO2. A balance of geological activity is likely beneficial, enough to drive cycles and field generation, not so much as to create continuous global volcanism that might make a world too volatile for stable ecosystems. Stable climate and star output. A planet needs time for life to evolve. Earth has had liquid water for almost 4 billion years through various climate swings. A star's output can change. Earth's biosphere and geology compensated, keeping the planet habitable. If the changes were more extreme, or Earth's feedbacks weaker, life might have been snuffed out. So habitability is a combination of initial conditions and subsequent luck and balancing feedbacks. When we look at exoplanets, especially those in habitable zones, we assess these factors. Does the planet likely have an atmosphere? What's the star like? We've identified some promising, potentially habitable exoplanets. Proxima Centauri, B. TRAPPIST, E, F, G, as mentioned. Earth-sized, in or near habitable zone around a dim star. Kepler, 452b, around a Sun-like star, often touted as older cousin of Earth, is larger, and the star is 6 billion years old. Interesting if it's rocky, but we're not sure it isn't too massive, having a thick atmosphere. Kepler, 2F and Kepler, 186f, are smaller planets in their star's habitable zones, though their stars are a bit cooler than the Sun. Many others have been found by Kepler and TESS that are unconfirmed or with limited information. Ultimately, detecting life is the holy grail. What might be a sign of life? On Earth, the combination of abundant oxygen and methane is a strong biosignature. Seeing both would raise eyebrows. Also, things like the spectral edge of chlorophyll could be a signature if we ever got a direct color spectrum of an exoplanet surface. Even seasonal changes in atmospheric composition could hint at biology. It's tricky because we have only one example of life's impact on a planet, Earth, and alien life might produce different gases. Also, non-biological processes can sometimes mimic biosignatures. So context is everything. We'd need to understand the planet's star, history, and environment to interpret signals, while the exoplanet hunt proceeds mostly via remote sensing. In our own solar system, we can go to these worlds to search for life or conditions. Mars is currently being combed by rovers and orbiters. Europa and Enceladus are top targets. Europa Clipper will orbit Jupiter and repeatedly fly by Europa to map its ice and composition, even scouting for plumes to sample for organic molecules. JUICE will explore Jupiter's moons and eventually orbit Ganymede, studying its ocean and magnetic field. For Enceladus, a future mission concept aims to directly sample its geysers for biomolecules and maybe even signs of microbial life. Titan will be visited by Dragonfly, a flying drone like Lander that will hop across Titan's dunescapes to drill into organics and look for prebiotic chemistry or even life's handiwork. Thus, our exploration strategy is twofold. Within our solar system, investigate all potentially habitable niches. Beyond our solar system, improve our telescopes to identify promising Earth-like planets around nearby stars and eventually directly image them. We stand at a moment in history where we can for the first time meaningfully search for life beyond Earth. Not long ago, planets around other stars was still hypothetical. Now it's routine science. The next leap, finding evidence of life's effects on another world, would be profound. It would tell us whether life is a cosmic common occurrence or a rare fluke. Either answer is deeply significant. If common, the universe may be teeming with biology and perhaps intelligence. If rare, then our pale blue dot is an even more precious oasis in a vast, perhaps mostly sterile desert. Future frontiers, exploring new worlds, and the fate of our planetary journey. What does the future hold for planet exploration? Both in continuing to explore our solar system and in reaching for others, the coming decades promise to be exciting. Within the solar system, several ambitious missions are on the horizon or in progress. We mentioned Europa Clipper and Dragonfly. These will illuminate the potential habitability of ocean worlds. Mars exploration continues. After Perseverance collects samples, a multi-part Mars sample return mission by NASA ESA aims to bring those samples to Earth by the mid-2030s, allowing labs on Earth to scrutinize Martian soil for signs of ancient life with far greater precision than any rover could. Plans for human missions to Mars loom on the multi-decade timescale. The 2030s or 2040s may see the first footsteps on Mars, fulfilling a dream long imagined. Humans could conduct science on Mars that robots struggle with, though robots will likely have already answered the life question by then. At Jupiter and Saturn, the next generation might be missions to actually land or sail in the oceans of the moons. A concept being studied is a Europa lander to drill through a thinner part of the ice, or a penetrator that melts its way down. Even more fanciful is a submarine for Titan's methane seas or an Enceladus ice drilling lander. These are technologically challenging, but so was landing humans on the moon. It's a matter of will and priority. There's also renewed interest in Venus. After decades focusing on Mars, NASA and ESA have recently approved missions to Venus in the 2030s, Da Vinci Plus and Veritas. ESA's Envision orbiter is planned as well. These missions will give Venus a fresh look, important for understanding how Earth, like planets, diverge. If Venus was once more temperate, when and how did it turn so hostile? We might find clues of past water or ongoing volcanic gases. Farther out, Uranus and Neptune remain the only major planets not revisited since Voyager. The US Planetary Science Decadal Survey has prioritized a Uranus orbiter and probe mission for the 2030s. This mission would journey for around 15 years to Uranus, deploy an atmospheric entry probe to sample Uranus's air directly, and orbit Uranus for a few years to study its rings, magnetosphere, and moons. Such a mission would be a bonanza of science. Understanding ice giants will fill a gap in our knowledge of planet formation. After Uranus, Neptune is a logical next target, potentially in the 2040s, possibly with a Triton lander or ocean finder included. These missions, though far off, underscore humanity's commitment to exploring all corners of our solar neighborhood. In the realm of exoplanets, as discussed, new space telescopes like JWST are opening windows. JWST has already begun examining atmospheres of some transiting exoplanets and even directly imaged a couple of gas giants. Over its lifetime, it might be able to probe some super-Earth atmospheres around nearer stars for molecules like water or CO2. The Roman telescope will find many cold exoplanets via microlensing and carry a technology demonstrator coronagraph to directly image a handful of known giant exoplanets, sharpening our skills. By the 2030s or 2040s, we hope to launch a large segmented mirror telescope. Such a telescope, armed with a coronagraph or a starshade, could directly see Earth-sized planets around perhaps dozens of nearby sun, like stars, and take spectra of them, searching for biosignature gases. Imagine seeing a pale blue dot in the sky of another star and detecting, say, oxygen, or even a color variation due to continents and oceans. That would be a civilization, changing discovery. We stand perhaps a generation away from that possibility. There are also imaginative projects like Breakthrough Starshot, which envisions sending gram-sized microprobes to Alpha Centauri using powerful laser sails, reaching 20% the speed of light to get there in about 20 years. While highly experimental, if such technology matured, we could potentially have flyby images of planets around the nearest stars within our lifetimes, perhaps revealing continents or clouds on an alien Earth. It sounds like sci-fi, but no more so than Jules Verne's moon rockets did in the 1860s. Human curiosity drives innovation, and the payoff, touching another star system, would be historic. As we explore, we also reflect. All these worlds we've visited in our minds, from Mercury's battered ground to Neptune's windy blues, have taught us about diversity and commonality. Diversity in that each planet is its own world with unique quirks. Commonality in that they are all part of one grand physical system, obeying the same gravity and chemistry, following similar stages of formation and evolution with variations on the theme. We've seen parallels, volcanoes on Earth and Io, sand dunes on Mars and Titan, polar lights on Earth and Jupiter, ice crusts on Europa, and our own Arctic Ocean. We've seen cautionary tales, a planet almost our twin that became a furnace, a small world that lost its shield and dried out. We look back at Earth with new appreciation for its perfectly tuned conditions, not too hot like Venus, not too cold like early Mars, big enough to hold air, spinning fast enough to have a magnetic field, blanketed by life that in turn helps maintain stability. The study of planets has also put us in our place. Copernicus removed Earth from the center. Galileo showed Earth is just one of many bodies. The last century revealed that even the sun is one of billions, and now that planets abound everywhere, our home is just one island in a vast archipelago of worlds. And yet, to us, it's special, the only known cradle of life. As we search for life elsewhere, we can't help but wonder about the rarity or ubiquity of life. Will we find biosignatures on Mars or Enceladus or an exoplanet? If we do, it means life might sprout wherever conditions allow, implying a living cosmos with many neighbors. If we don't, it could mean life is a freak accident, a cosmic miracle unique to Earth. In that case, the responsibility on us as stewards of the only garden of life increases immeasurably. Either way, studying planets has given us a cosmic perspective. Carl Sagan's famous pale blue dot speech encapsulated it. All of human history played out on a mote of dust suspended in a sunbeam. Every planet we visit reminds us of the fragility of habitability, how thin an atmosphere is, how delicate a balanced climate can be. We see Venus and fear a runaway greenhouse. We see Mars and fear the loss of a magnetic field and atmosphere. We turn those lessons to our own situation, recognizing our planet's climate is not static, that pumping greenhouse gases can push Earth toward a new, possibly unfavorable state. The barren surfaces of Venus and Mars urge us to be careful, lest Earth follow their paths in some distant future by our own doing. Planets also teach resilience and change. Earth has gone through mass extinctions and recovered. Life has a tenacity. Who knows, maybe life exists in some form under the ice of Europa or in Titan's chemical stew, very different from Earth's biology. If we find even a second Genesis in our solar system, it means life is a cosmic imperative. If we don't find it nearby, we'll keep looking outward. Ultimately, the exploration of planets is a human story of curiosity, wonder, and reflection. We have gone from gazing at wandering stars to sending robot emissaries across the void to stand on those worlds and report back. With each step, we've been awed. We felt the volcanic heat of Io and shivered in the methane rain of Triton. We marveled at Saturn's rings, countless icy particles orchestrated by gravity into one of nature's most gorgeous sights. We flew through a geyser on Enceladus and tasted primordial water. We watched a sunset on Mars through the eyes of rovers, its sky tinged butterscotch by fine dust. These experiences, albeit through our mechanical proxies, have enriched our soul and expanded our imagination of what worlds are out there. Looking up at the night sky now, we no longer see just pinpoints of light. We see other suns with their own planets, perhaps a giant with storms bigger than Earth, or a warm ocean world enveloped in clouds, or a rocky orb struggling to hold onto an atmosphere. We might even see lights of another civilization, though none have been detected yet. The possibility is there, made real by the sheer number of planets. So we end our journey where we began, under the stars. But now, when we point out the wanderers, our neighboring planets, we do so with understanding and kinship. The word planet means wanderer, but ironically, planets also taught us how connected everything is. Wanderers though they are, they orbit in a family, influencing each other and their star. And we, wanderers ourselves, have begun to venture from our home to visit them, first with our eyes, then with our ships, someday perhaps in person. The story of planets is the story of cosmic islands and the voyages between them. It's a tale of creation, how dust can clump and ignite and then leave residue that becomes worlds both barren and lush. It's a tale of destruction and renewal, giant impacts that can destroy worlds or birth moons, atmospheres that can collapse or run wild, but also life that can emerge and transform a whole planet. It's a story that forces us to ask, how common is a world like ours? How rare are we? and where do we go from here? In the next decades, we may finally get an answer to, are we alone? By detecting life signs elsewhere. Or we may find that Earth is singular so far. In either case, planet exploration will continue, driven by the deepest human urges to know and to go. Unmanned or manned, we will likely set foot on Mars, dive into the seas of Europa with submersibles, maybe float in the atmosphere of Titan or Venus in balloons. We will refine our techniques to image Earth like exoplanets. Perhaps one day, far in the future, our descendants will build starships to visit neighboring systems, turning those points of light into landscapes beneath their boots. As our perspective broadens, our appreciation of Earth deepens. The pale blue dot that Sagan spoke of is our only home in a vast cosmos, at least for now. The other planets show starkly that Earth's hospitality is unique in our solar system. So exploring other planets is not just about them, but also about us, holding a mirror to Earth. We see what happens when greenhouse gases go unchecked, or when a small planet cools and dries, or how a protective magnetic field can preserve a world. These lessons are invaluable as we manage Earth's future. Finally, there is an almost spiritual aspect. By understanding planets, we come to understand our place in the universe. No longer are we the center, we are part of something vast and magnificent. The diversity of worlds out there suggests that if life could arise here, it could arise elsewhere. And if it hasn't elsewhere, then we carry an enormous responsibility as the sole known bearers of consciousness to care for our oasis and perhaps spread life beyond it. We began this journey with the ancient wanderers in the sky. Now, having explored the fire of the inner planets, the grandeur of the giants, the ice of the dwarfs, and even peered to the worlds of other stars, we end with a renewed sense of wonder. The night sky will never look the same. Each dot is a sun, many with planets, some perhaps with beings looking back at a tiny sun pinprick that is our home. The voyage of planetary exploration has really just begun. There are new horizons to reach, literally, as with the probe New Horizons at Pluto, and profound questions still to answer. But one thing is certain, our curiosity will not cease. We will continue to wander, in person or by proxy, mind and body, outward to the planets and beyond. For in seeking these other worlds, we ultimately seek to know ourselves and our place in the cosmos. It is a grand story, one that spans from the fires of creation to the potential spark of life, and it's a story with no end in sight. Each planet we visited, by telescope or spacecraft, has left us changed. They have shown us beauty beyond measure, forces beyond fear, and resilience beyond expectation. In their extremes we find meaning. Mercury's day, night cycle, whispering that too much heat and too little air yields desolation. Venus's clouds warning how quickly paradise can be lost. Mars's dry rivers reminding that climate can turn on a planet. Jupiter's storms humbling us with their power. Saturn's rings teaching the elegance of gravity's order. Uranus and Neptune revealing that even on the edge of darkness, winds still dance. Pluto and its kin proving that even small worlds can be geologically alive. As we continue to learn, we should also take a moment to feel the awe. We are fortunate to live in a time when the long-lost siblings of Earth have been revealed in all their glory. A human from just 100 years ago could only dream of what we've seen. And a human 100 years from now might walk on Mars or float in a Europa submersible, living our present dreams. Our quest for knowledge and exploration binds the generations in a common continuum of discovery. So, step outside on a clear night. Find Venus blazing in the west or Jupiter rising in the east. Know that you're looking at entire worlds, places that we've now touched with our robotic emissaries and, one day, might touch with our hands. The sky that was once the realm of gods and myth is now open to us as a realm of nature to explore. The wanderers are no longer distant mysteries. They are destinations. They have become real places with landscapes and weather and histories we can narrate. And in exploring them, we've woven their stories into our own. We too are wanderers. As Sagan said, we began as wanderers, and we are wanderers still. We have lingered long on the shores of the cosmic ocean, but now we are setting sail among the stars. In the end, the study of planets teaches us humility and unity. All those worlds out there, and here we are, one small crew on spaceship Earth, sailing together through space and time. The pale lights of Mercury, Venus, Mars, Jupiter, and Saturn in our sky are like signposts, telling us where we've been and where we will go. When we finally decipher the secrets of alien atmospheres or find microbes on a distant moon, it will underscore that we are a part of this universe, connected to the planets and stars around us. We are not apart from nature. We are born of the same processes that birthed the planets. The voyage will continue. New rockets, new telescopes, new generations of scientists and explorers will carry the torch. They'll answer questions we haven't thought to ask, and surely encounter surprises we haven't imagined. Planets will continue to fill us with wonder, whether it's weird new exoplanet types or hidden oceans discovered under icy crusts. Each answer will likely raise more questions, as is the way of science. But that is a joy, not a frustration. It means the adventure of discovery is endless. There will always be another horizon, another world to learn from. And as long as humans have eyes to the sky and minds that dream, we will be out there, exploring, moving outward, one world at a time, forging connections across the darkness. In a sense, by exploring the planets, we are the universe exploring itself. Matter that became life, life that became intelligent, now reaching back out to understand the grand mechanism that produced us. Every footprint left on the moon, every photon counted from a distant exoplanet, is the cosmos coming to know itself through us. Our journey through the planets has thus been a journey inward as well, into the nature of who we are and what we may become. When future explorers stand on Mars and look up at a sky with 2 moons, or when a robotic probe sends back the first images from an Earth, like planet light years away, the sense of connection will only grow stronger. We'll realize ever more that we share the universe with all these worlds, and maybe share it with other life. For now, we cherish our pale blue dot while reaching for others. We end our tour back on Earth, gazing up, but with new eyes. The wanderers in the sky are no longer distant gods, but places we know. Siblings in the solar family, each unique, all kin. We have walked among them in our imaginations and through our proxies. Soon, we will with our own feet. The story of planets is ultimately a celebration of human curiosity. We dared to ask ancient lights what they were, and we answered, revealing a universe richer than our ancestors could have believed. Stand under the night sky and feel that connection, tiny though we are. We understand those points of light now. Mercury, Venus, Mars, Jupiter, Saturn. We know them intimately. And far beyond, around myriad stars, countless other planets circle, waiting for our discovery. The wanderers will guide us outward, and wherever we go, we will carry the legacy of understanding forged here at home. In that sense, the journey of exploring planets is a journey of self-discovery for humanity. We set out to find new worlds, and in the process, we found ourselves, one people on one world, learning that the cosmos is full of worlds. It is perhaps the grandest revelation of all. The planets have taught us that the only borders are those we create ourselves. In the cosmos, all worlds share the same sky. The wanderers still move across the heavens as they did for the ancients. But now, when we see them, we greet them as familiar friends, places we've been, or soon will go. And as we trace their paths, and even send our emissaries to dance among them, we too become wanderers beyond the Earth, united in the eternal quest to know the universe and our place within it. The story of planets, our story, continues, onward and outward, under the cosmic sky that we all share.